Thank you.
Good morning to everyone. Thank you for coming. Thank you, Asunción, for inviting me to give this challenging talk. It is, in fact, well, Asunción told me to talk about the sulfur in the solar system. I said, no, I don't work on sulfur chemistry. I don't know anything about sulfur in the solar system, only some bodies, volcanic eruptions on Io, the interior. And in principle, I said, no, this is going to be very difficult for me. But then I started reading, and I said, OK, I may say something, because there is material to explain what is happening with sulfur in our planetary system. So this is what I did. I don't think I will need the 30 minutes. I never know. Maybe I go quick and it's 15. Maybe I relax, and then I reach the 30 minutes. So as she said, I'm coming from Granada. You know where we are. This is our center. And I will do a kind of traveling along the solar system with the different planets. I'm not going to talk about asteroids, minor bodies, comets, only the planets, and even not the, let's say, the trans-Neptunian objects that we don't know basically anything about them on their composition on the interior. So this is Mercury. This is the closest planet to the solar system. Mercury has not a proper atmosphere. Whatever we see like a gaseous component involving the planet is coming from what is an exosphere and is produced by sputtering. The measurement in situ by several missions, the last one Messenger, even when you see the planet in optical wavelength, you see, or visible wavelength, you see something which is very gray. But when you do some study with basically gamma ray spectrometer and thermal emission spectrometer, you see that there is a different composition in different areas connected to the craters and also to the material in here. The sputtering processes gives rise to exosphere in this shape. It looks like a little bit like a comet. You have the solar wind and the particles from the sun, which are very heavy, or are protons, impacting on the surface and really taking out the atoms and producing this temporary exosphere. So because Asunción wanted me to talk about sulfur and the composition of sulfur in the planets, then I tried to see how much of these different colors are linked to sulfur when you do gamma ray spectroscopy. See, this is kind of a lot. So this is what I took from some of the papers. These colors indicate the different composition of on the surface. And I don't know if you see, because I don't see with these glasses, but you see that here is sulfur. Why sulfur is quotient, is a ratio with silicon, is simply because the studies, they don't give an absolute number of S atom or mass with the measurements. So you have a kind of quotient between sulfur and some other species, calcium, magnesium, and this is what you see. So the surface is heterogeneous, so whatever it happened or how the planet formed is really reflecting heterogeneous processes. Mercury, you know, that has no mantle. That basically is the surface and the core. The mantle seems to be stripped away because of a large impact. And the numbers, which I don't see, but these are I computed the number or the mass of sulfur with these results in here and also in this table. And maybe with a large, let's say, or some uncertainty, this is the amount of sulfur that we have on Mercury surface and core. The mantle is stripped away by an impact. Because for understanding or for analyzing the measurement, you have to do some assumptions. So this is the work I showed before with some values for the core, which is 20 kilometers in radius, the density of Mercury, and then we have to assume a percentage of mass in sulfur, and this is the number of kilograms, 10 to the 10 of S in Mercury. Because also you have a margin when you analyze the data, you can also assume that the percentage of weight in sulfur is at 20%, and the number is higher. I did this number because Asunción told me at the beginning that she wanted, or she would like to have a bulk sulfur, let's say, abundance in the solar system compared to some other protoplanetary disk. So I tried to do in the case where I could. In some other cases, I was not able. So at the end, we have Mercury, which is a very small, let's say, body or planet. This is the number of kilograms in sulfur in the Mercury core. The mantle is only 200 kilometers. This is going to contribute very little, and the surface basically is nothing when you compare to the core. So this is the case for Mercury. And the atmosphere, in fact, there are very few detections of S atoms, and this supports that the amount of sulfur on the surface is very little when you have these sputtering processes in the exosphere. I forgot about the Earth, so I just put it yesterday night. The Earth, you know, that is 6,000 kilometers in radius. So most of the sulfur in the Earth is located in the lithosphere. And also because the systems of the oceans, you have sulfur dissolved in the ocean. So you have here, if you see, because I don't, you said the atmosphere, there is basically nothing, 10 to the 9, I think. But then if you go to the lithosphere, when you conclude, or you include igneous rocks, metamorphic, sedimentary, you have about 10 to the 19. So the Earth is having a lot of sulfur in the crust or in the lithosphere, and basically nothing in the atmosphere. The volcanic eruptions, which are coming from this region, obviously contribute very little to the atmosphere, and also the chemical lifetime of sulfur in any planetary atmosphere with UV radiation is really very short, so you destroy it. For the case of Mars, which is another rocky planet with a very tenuous atmosphere of carbon dioxide, CO2, these are measurements from gamma ray spectrometer, the same technique as for Mercury. And also we see again that Mars surface is heterogeneous. This is for the gamma ray, this is for thermal emission. And well, I don't know if you see the numbers, I don't, but the numbers here in weight is about 2% in weight, which is very similar. If you remember, Mercury is about also between 1.5 and 20, according to the uncertainty. Again, we do, I think it's already published, yeah. So with these results in here, with this kind of diversity on the surface of Mars regarding sulfur, there are computations by some authors. I think it's not here, all these researchers, and they conclude also the amount of sulfur that there is on the core of Mars, on the primitive mantle. Also, Jose Maria will talk about meteorites maybe coming from Mars and the composition that is in there. So the numbers in here is a little bit higher than Mercury, but considerably lower than on the Earth. So I think the last slide contains a summary of all the numbers to see the amount of sulfur in the solar system. In the case of Venus, oh, sorry, this one. Anyway, they should be both at the same time. So Venus is considered like the twin sister, twin sister is a lady, twin sister of the Earth. It has a very thick CO2 atmosphere. The surface of the pressure of the surface is 90 bar and a temperature of 700 Kelvin. Is similar size to the Earth. There is a very rich, let's say, chemical soup containing sulfur on the atmosphere of Venus, on the surface of the atmosphere of Venus. And these chemical, let's say, processes produce a very thick layer of sulfuric acid and clouds that is obviously impeding the vision of the surface. The image here is from radar, and this is one of the highest volcanoes on Venus. There is still, Venus is volcanically active, and it's not sure if there is or there are tectonic plates, but there are volcans. So the case of Venus has been explored by one mission or several missions. The most, let's say, rewarding were the Russians. They got plenty of information together with a ESA mission, Venus Express, and there were some models developed by Vladimir Krasnopolsky, and here you can see the profile of some of the species, SO2, OCS, SO. I didn't put the chemical network because it's really complex, and the models basically are photochemical model out of equilibrium and are also are only basically valid above 50, 60 kilometers. Below this altitude, the pressure is so high and the temperature is so high that you have to do thermochemical models, which are simpler than the photochemical model, but this author didn't do it. So again, I tried to get the amount of sulfur in the atmosphere. These are the numbers I get from, I take the mixing, well, the results in here, the mixing ratio for each of the species, the kilograms, the integrated column of sulfur, the percentage in weight, and then I took into account the stoichiometric formula, and I get that in the atmosphere, this is an upper limit because you see the concentration decreases with altitude, so the amount of sulfur is 10 to the 15 kilos. But of course, I have to add the one on the planet. And this is if we still assume that it's very similar to the Earth, not only in evolution, well, different in evolution, but size and distant to the sun, then I take basically the same number that for the Earth, and then I apply only just a small correction factor for the size. So this is the amount of sulfur on the surface, which, because of volcanic eruption, is going into the atmosphere in this value. So this is another number to have in mind of sulfur in Venus. And these are the only 3 planets where I can derive some numbers for the sulfur, because the other ones, you will see the giant planets is below the cloud deck, and I don't know. As I said, I didn't do anything about the asteroids, so I go to the giant and icy planets. This picture is on a scale. This is Jupiter. These are one of the most recent images of Juno, the mission which is there. You may say that why here is blue and then orange. I mean, Juno is providing very nice images of Jupiter, but they are really very much dedicated to outreach. The scientific information is only related to dynamic, not so much to composition. But nevertheless, they really stretch the images to obtain these different sun and belts. This is Jupiter, one of the images by Hubble, where you see a storm developing at the northern hemisphere, the rings. This is Uranus. Uranus, I don't know if you know, that is rotating, like tumbling around, maybe because there was a large impact at the early formation of the planet. And this is Neptune. So these are the 2 different colors. These are more rich in carbon, and you get a high, and the metallicity is much higher than Jupiter on Saturn. These are the interiors, and most likely, I think that Diego will say something about species in the interior. So the case of Jupiter and Saturn, you have a rocky interior where most likely we might have accreted the planetesimals, which were at that time rich in the atomic or in the elements in the solar nebula, could be enriched by some factors, could be, I don't know. But these are the 2 cases for Jupiter and Saturn, and these are the composition, or approximate, because the only thing we know is the rotation, angular momentum, and no measurements. Only for Jupiter there was a probe entering in a region which was really very hot compared to what they wanted to measure the water. It's the Galileo probe mass spectrometer is entered around here. So these 2 are gas giants. So you have a tiny core which is solid or metallic or some curious state of hydrogen or water. And these 2 are Uranus and Neptune. They were called or named up to now icy giants, but the recent measurements and studies, they call fluid giants, because it's thought that they have between the rocky core and the dense atmospheric layers, the bar or millibar or kilobars, there is something, a liquid, could be water with some ammonia and some other species. So this is the structure, the thermal, I mean, these are models, I think they are, yes, these are thermochemical models for keeping the icy planet, but it should be fluid. The Jupiter, Saturn, Uranus, and Neptune. You see that, I will tell you later the thermal structure of each of those. But these studies, they are coming from thermochemical model because they are going to very high pressure level of more, I mean, this is, I think, 1,000 bars in here, 10 or so. This is, well, here you can apply thermochemical model. A thermochemical model, you only minimize the free Gibbs energy. You consider an elementary composition, which could be solar, supersolar, or solar. You minimize the free energy. You also allow the code for condensation. They are available, so we can do. And in the case of Jupiter, you see that there are clouds of water. There is cloud of ammonia sulfide, or sulfide ammonia, and also of ammonia by itself, I mean, only ammonia. The case of Saturn, you see that the clouds can go deeper, because the temperature is colder than in Saturn, so the condensation occurs at deeper level, but again, you have the same structure in clouds. And here you have already Uranus and Neptune, which are even colder, and you have H2S in cloud by itself. You don't only have the sulfur attached to the ammonia clouds in this form, but also in here. These are models, so that it has not been measured. We don't know how much sulfur, atomic or elemental sulfur, is in there, so these are models. But these tell you that sulfur is existing in this atmosphere. I have to say also that sulfur, none of the sulfur species that you may expect, S2, SH, OCS, CS has not been detected in any of the planets above the tropopause, so which means what we already know, that the sulfur is condensing in these layers. Only one case, Neptune, there were measurements by ALMA, the radio telescope, and they detected CS. So CS is not produced, or the production by thermochemical model is very low. When you reach the cold trap, which is around the 1 bar, it condenses. So the conclusion is that the CS detected in Neptune comes from an impact of a comet. Maybe Dominique will talk about that. So there was a cometary impact, I think it was 4,000 years ago, and the sulfur delivered in this impact is still alive or remaining in the atmosphere of Neptune. This is the thermal structure, as I said before, of these 4 planets. This is Jupiter, and below, well, this is altitude, but this is 0 kilometer is 1 bar pressure. So Jupiter is much warmer than the other planets at deeper layers, and that's why the sulfur is not really present by itself somewhere, but it's also attached to ammonia or NH4. And this is the structure of Saturn, which is similar to this one. Uranus and Neptune, although they diverge in here, or they are not similar, currently all the models assume that they behave completely equal below this pressure level, which is 10 or 20 bars. Again, you have purely H2S clouds in here, according to models, but it's not measured. Hello? Here. So if we go more in detail, and I did also some computation by myself, this is the Jupiter atmosphere. This is the thermal structure. You see that it's up to, I don't know, 400 Kelvin, but if you go deeper, can reach almost 700 or 800 Kelvin in the deep atmosphere. And then with these elementary abundances in Jupiter versus the sun, or protosolar or solar, I did very simple thermochemical computations. And this is the mixing ratio of H2S. And obviously, let's see if I don't make a mess. Yes, this is pressure, so this is the deep in the atmosphere, is 10 to the 4 bars, and this is a 2 or 0.1 bar. This is around the tropopause. Even the thermochemical calculation, when I put condensation in here, they disappear. So basically, it's telling us that the H2S condenses in this level, and the very simple model can reproduce it. With these results, I didn't dare to do any number of sulfur content because, although we know the pressure where the clouds exist, I don't know the depth of the clouds. I have to integrate along all the planets, so any number that I could give would be really very much affected by errors and by my ignorance, let's say, lack of knowledge. There was a mission, the Galileo mission, that the final, say, scientific achievement of the mission was measuring the atomic abundance of the species in the entry site, on the penetration site. These are the numbers that they measure, and it was able to know sulfur among them, oxygen, some noble gases, to know how the deep interior of Jupiter could be made of. And this is the only reference we have for the giant planets. And here in this table, or in this plot, is shown. In the case of Saturn, the thermal structure is very similar to the one of Jupiter. Maybe there are less variation around the tropopause. These are very recent measurements for the Cassini perspective, so these are not Voyager or for ground-based observation. The thermal structure is very variable in different altitudes, and again, computing models, you have the location of the clouds, which is ammonia, and you have also the sulfur is incorporated in here. This is purely ammonia, and this is water ice. If you compare here, I wanted to put the comparison between the knowledge about the elemental abundances of the different planets. This is the case of Uranus and Neptune. We only know the abundance, the measurement of, estimate this measurement, but it's difficult to say if it's real, accurate for carbon. So carbon, in the case of Neptune and Uranus, is supersolar, around 100, but we don't know anything about the other species. Jupiter, because of the probe, of the Galileo probe, is very much documented, and here you see the numbers, and these are the solar values. So the good point, or let's say the key point of this plot is to see that once you know the elemental abundance of the interior, of the core of the planets, you more or less can know or guess the origin or how they form. In the case of Jupiter, these values of the abundances refer to different formation processes that more or less you can ascertain how Jupiter was formed, but in the case of Saturn, because there are only a few measurements of carbon, very little about nitrogen, which is in an upper limit, and the sulfur is not very much constrained. So these are three different regions. I mean, if you have values, I mean, abundance compared to the sun around 10, it tells you how the Saturn was formed. If you have it in this region, it will give you information about how it is, and with this region, if it's only evaporation, I think, of ices. So the key point is that we have, in the same way that you measure the Jupiter elemental abundance in the interior, you should do the same for Saturn. And if possible, to constrain nitrogen, sulfur, and oxygen. This will give you a much more reliable information how the planet was formed. This picture of this conclusion is even more difficult to ascertain in the case of Neptune, where we know nothing. And although there will be mission to Neptune, Uranus by NASA in the next decade, it's not going to be the case for Neptune. So this is Uranus and Neptune. These are what I said before, the fluid planets. And these are different images from Voyager, Uranus, and Neptune. They are all images by process with new techniques. Here you see that, as I mentioned before, the case of Neptune, which is tumbled or tilted on the rotation axis, Uranus, and these are different regions. These enhanced images basically show the dynamics, and this dynamic of the atmosphere is connected to the cloud layers that are placed below the 1 bar. So for Uranus and Neptune, this is the thermal profile that we normally consider, although it has not been measured. We only constrain by observations. And again, you have the liquid. That's why they are fluid now. It's liquid water plus ammonia. You have a core, the ice. Then here you have the same cloud as before, the NH4SH, but here you may have also NH2S purely, and methane. Methane is supersaturated, is measured in the case of Uranus and Neptune. There is a very good paper by Olivier Moussis and collaborator in 2020, Space Science Review, where he or they analyze how this elementary composition, sulfur, nitrogen, oxygen, carbon, noble gases, could be compared to the different formation of the planets. I mean, this instability model or the core accretion model. So you can end up with subsolar metallicities or supersolar. So this means that unless we measure the elementary abundance in these two planets, at least for Uranus and Neptune, we cannot be very sure how they form and if there was a competing processes or if it was a mix of both of them. Yeah. So this is a very similar, a work very similar to the one I showed before. It's done by Ricardo Hueso in 2020. And again, you have the same structure. This is also, in every case, because we don't know how much enhanced compared to the solar values there are in these two planets, they did different models increasing the ammonia at 2 times the solar value or 10 times. Basically, the structure is about the same. You have the clouds maybe higher in cloud content, for 80 times solar abundance or 10 more ammonia. Ammonia is a cooling agent in the atmosphere for forming the clouds, and also the interior of the planet with the water, ice, and the liquid. So basically, these are models that the assumption is in here. We don't know how much we should put in there, and that is what we should measure somehow and somewhen. Hey. And I think, yeah, okay. So this is what we normally use when we want to do kind of any model regarding the interior or the deep layers of the atmosphere with thermochemical model. Because photochemistry, you have to include the solar radiation, and then you have to break the molecules and to know the causation. So in principle, if you want to know the interior, and in the case of the sulfur is not going to exist about 1 bar. So these are the values of elementary abundance compared to the sun or protosolar, and this is what we consider. So you see that basically sulfur, we think, or they think, Sashi Atreya and collaborators think that the is very much enhanced in Uranus and very little in Neptune. So this is an open question that we don't know how it's going to be solved. Why they are not so far from each other? Well, I mean, they are in the outer solar system, but why Uranus is so dense in sulfur, and why not in the case of Neptune? Maybe the formation, this instability, or accretion, or a mix of both. So the message I want to send, because I don't dare to write conclusion, I cannot conclude anything, mainly because it's not my field, and I have tried to put together the information I could dig out. So is that in the case of rocky planets, like Mercury, here it should be Mars that I forgot, and Earth and Venus, the sulfur is on the crust, on the mantle, if there is mantle, on the lithosphere, and the atmosphere contains very, very little sulfur. In the case of Jupiter and Saturn, the Jupiter measurements are reliable, so I can derive a number which is very much affected by uncertainty, but in the case of Saturn, we need to know how much of these atomic species and noble gases is in there for constraining the origin and also the content of sulfur in the solar system. And in the case of Uranus and Neptune, here you have several cases, and if you consider that the deep interior or what is happening, I mean, the release, the atmosphere or the gaseous component of the planet comes from the volatile release, you will have a subsolar value. If the planets form according to the disk instability, you have the protoplanetary disk, you have an instability, and then you start to accrete material, you form the planet, you have these values which are below 100. But if you have amorphous ice with some components trapped inside, you will have these supersolar values. And these are the two lines corresponding to two different processes. In the case of sulfur, the determination of the value has to be very accurate because the difference is only 93 in one case, which is here, and 115 in there. And this will tell you, obviously, how much sulfur is in the interior of these two planets and how they form. And this is all what I have to say. Yeah. So this is a flyby of Saturn.
Thanks for the talk. So maybe it was not expected to be included, but do you know anything about the abundances of sulfur in the satellites of Jupiter or Saturn? Are they expected to be similar to the planets?
We know that, sorry, I have a loud voice. I forgot Io, you know, yeah, I forgot Io. Io has strong volcanic eruptions, and these eruptions, they are basically sulfur in the different, with oxygen. So it's not H, it's SO2, SO3, atomic sulfur, well, atomic bimolecular S2, S3, S4. This is what is on Io, and you see that the eruption is clearly detected. Even if you take a spectra not on volcanic regions, you will see the deposit of sulfur. So it could be this is the deposit and is not properly on the surface. Europa, when you took a spectra, you have salts which contain also sulfur. Ganymede and Callisto, we have not seen any feature related to sulfur. Maybe we will see in the future, there is a mission going there, launching next year, JUICE, so maybe we see something in there. But the exosphere surrounding Io, because of the volcanoes, is SO2. In the case of Europa, is water, oxygen, and this is coming from the photochemistry of water, either on the ices on the surface or already out gases, but the sulfur is on the salts. So you take a spectra, you see the fractures of Europa, and there you see salts with a signature of sulfur. Ganymede and Callisto, nothing. Nothing from ground, maybe there, yeah?
Thank you.
Very good talk, thanks for all the review. I have the feeling that it's important to mention that the sulfur is in fact a highly hydrophile element, that for all these bodies that were melted was in those cases were going directly to the core with the iron nickel. And particularly in most of these cases, particularly for example for the giant planets, we have a very significant flux of meteoroids, asteroids, comets that are hitting the top atmospheres of these bodies. This process has a really important input in sulfur, because all these undifferentiated bodies, as I will explain in next talk, play a significant role just delivering continuously this sulfur, no, in the materials. A particular paper summarizing all our knowledge about the different elements, elementary abundances, is Anders and Greves, 1989, that is a compilation of the CI composition of meteorites compared with the solar composition.
Yeah, when you have a comet entering into a planet, because you know it's highly porous, so it will be basically it will be destroyed before reaching the 1 bar level. So any molecule, in fact, when you have a comet which is 99% water ice, or 90% water ice, 10% carbon monoxide, and 8% carbon dioxide, and the rest are minors, during the shock impact, you destroy the water, and then the carbon of the CO and CO2 goes into some other molecule. One of them is CS. So the case of comets is very well known. But basically, they vaporize in 1 millibar level. They don't reach deeper levels. The case of more solid component like asteroids, I don't know how much sulfur they have, and because they are more, let's say, solid, they have no porous interior, they could survive to deeper layers. But compared to the huge core of Jupiter, obviously they bring sulfur, but I don't think you can really change a number in a 10% or 20%. You need a very high impact rate, which is not taking place. The case of Neptune, as I said before, CS was detected. We did plenty of chemical modeling, photochemical, thermochemical, and it shouldn't be in the thermosphere and in the stratosphere. So we concluded that it was an impact happening 4,000 years ago. But the point is that when you put something going into the planet, it will really vaporize at 1 millibar level if it's a comet, or maybe 1 bar level if you reach 1 bar level for asteroids.
Yes, of course, but it remains elemental sulfur in the atmosphere.
Yeah, it remains there. Yeah.
And particularly when are undifferentiated bodies of asteroid nature, most of this sulfur is forming part of troilite and pyrrhotite that are particularly refractory, so they can survive in the atmosphere as well. So it's
okay, thank you.
Thanks.
More questions? Diego.
It's mostly a comment to follow up on this. Basically, we did this kind of reasoning for when we were working on exoplanets and starting to formulate the Ariel mission. If basically what we see in the atmosphere of exoplanet is going to be really what is there, so the signature of how they are composed, or if it is a contamination by comets and impacts. Basically, what we saw, based also on the case of Jupiter and the impact of comet Schumacher-Levy, it seems that if they are small bodies, they tend to be vaporized very quickly, and you will see them, I think, above the tropopause. And they will not contaminate the atmosphere, so they will not reach the level where you do spectroscopy and you can probe the composition of the planet. If you instead look at the higher level, you will see the contaminants, and in fact, for example, the water in the atmosphere of Jupiter above the tropopause is thought to be still connected to the impact of Schumacher-Levy. So if you look water at very high altitude, it is the water of the impactor and not from from
interior,
Jupiter and from the interior. Instead, in the proper atmosphere below the tropopause, you don't reach this level. If it is a larger bodies, it will penetrate deeper. It can go a few thousand kilometers. That was the case of Schumacher-Levy. They think that it exploded somewhere around between 2,000 and 5,000 kilometers deep. So basically, you contaminate lower level. You will see an upwelling that brings the material, but they will recondense and disappear because the impact of Schumacher-Levy. They saw, for example, metals and sulfur in the atmosphere of Jupiter for a few weeks, most of 3 months, and then they disappeared again. So the knowledge at the moment, the rule of the thumb seems to be you can see these impacts and you can see the contamination, but it's going to be temporarily localized. At the moment, for our giant planet, it doesn't seem the flux is so high to permanently contaminate the atmosphere.
No.
For exoplanets, it could be different, because if you have a larger population of sun-grazing exocomets, then you can have larger fluxes, but that's still a big question mark.
Yeah, we have been doing some computation about what we call exogenic material on giant exoplanets, and in all the models we have run, together with Denis Juliak, a postdoc in Granada, because the turbulent transport is so effective that wherever you, let's say, deposit it in 1 millibar or 10 millibars layer, is because we were looking for signatures and how to detect that from spectroscopic measurements. So because the and we have 1D model, we don't do 2D. Because the turbulent transport is so effective and the chemistry, even photochemistry is so quick because the high temperature, the signature disappear in weeks. So either you are lucky to have a exocomet impacting an exoplanet and you just take the transmission spectrum, or we are not really going to be very lucky right now. This is true, there are planets close to the star. If you go farther away, the temperature is colder, the turbulent transport is less effective, and maybe you are by direct imaging or spectroscopy with James Webb, you can see something. But this is the thing. In the case of Jupiter, that's why the water is still mixing all the time. I mean, after 12 years, no, 94, 18 years, the water you see in the stratosphere of Jupiter is coming from Schumacher-Levy, and is still distributing along the planet, not only in the same latitudinal region, but also is moving because it's very dynamic. Yeah. So, I mean, there are so many things to do.
I have a very naive question, I think, because in Venus, the chemical composition is very similar to a comet, I think, no? Because you have S3, S4, and...
Yeah, but these are, if you saw, I mean, Venus is carbon monoxide 90%. So the atmosphere is CO2, like Mars, is 90 bars. But the abundance, the relative abundance on Venus of these sulfur species is in part per million, part per billion, 10 to the minus 9, 10 to the minus 3, is much lower than, well, I don't know how much sulfur has a comet, but it's not so low. Yeah. But this is volcanic origin. This is volcanic. It's volcanic.
Okay.
So you have the volcanic eruption or the surface, or even the lava still
I was thinking that in some sense Venus has kept the initial composition or something like that.
No, maybe it suffered also the big late heavy bombardment, and we don't know how many of these elementary components coming from this period of comets are retained in the planets. Yeah. But the sulfur in Venus is minor, is very minor, is in the part per million, part per trillion or billion. Yeah.
Okay,
It's not
thank
cometary.
you.
Even a comet cannot reach anywhere, so if there is an impact of a comet, the atmosphere is so dense that it really will not go deep. Yeah.
Okay. Thank you. Let's move to the next speaker, that is Josep Maria Trio.
Okay. So the title of my talk is Where Was the Sulfur? Lessons from the chemical composition of meteorites. As I was saying, we have made this at the Institute of Space Sciences in Barcelona. So, and I dedicate my talk to all my colleagues of the UNSMET Antarctic Search for Meteorites that allow us to get in the ICE collection pieces of really pristine bodies that has been recovered in Antarctica. And this will be probably one of the hot topics in the talk, the discovery we made and published in Nature Astronomy about a xenolith of an ancient body, probably a comet, that is in fact containing really amazing chemistry on the outer protoplanetary disk. So the basic outline, I will describe very briefly early evolution of the protoplanetary disk, what we know, the real complexity of the early gas phase environment and how this changed over the heliocentric distance and over time, of course. Then I will make some general overview related with condensation of the origin of planetesimals and cometesimals. Mostly condensation from the vapor phase was the main source of materials that finally ended building planetesimals and cometesimals. And the first 10 millions of years in the evolution of the solar system is a continuous fight between accretion versus disruption of all these bodies, because these building blocks, these primordial bodies that were formed in such a early stage of our solar system really was marked by continuous collisions, continuous processes of decaying in their orbits towards the sun, vaporization, and other processes that were finally producing the undifferentiated bodies that we know and we have now in our laboratories. Okay. So I will give you some examples of some chondrite groups and particularly describing the most hydrated groups that can give additional clues about the sulfur. And I will describe this discovery of a xenolith in La Paz 02342 chondrite. This is a unique sample from the other protoplanetary disk and probably opens a door to future amazing discoveries in the interiors of these really fine-grained matrices of this type of meteorites. And particularly this class, this xenolith, is talking us about the early accretion of sodium-rich sulfides, carbonates, and clay minerals in the outer part of the protoplanetary disk. So just going little by little, planetesimal formation is the first part. Just during the proplite early evolution, we have that the early solar system gas drag produced a very fast migration of bodies. Depending on the heliocentric distance, this is a diagram by Van Beukel in 2007, in which we have not in a scale. Please realize that this is 1/3 of the Earth-Sun distance. In this region, in fact, we will have the effect of a really strong magnetic field of the protosun, and depending of this distance at about 10 astronomical units, we will have the so-called snow line. So from here, the water will be dominating the condensation of ices, and of course, a little bit far away, you have also methane, ammonia, so at the end, it's a big mixture of all these ices as well. So in this region, you have condensation and aggregation of cometesimals. In the inner part, where most terrestrial planets are, in the inner part of this distribution, you will have the condensation of metals, silicates, and all these were in fact going on over a continuous infall of materials, also from the other part of the disk, that were quickly evaporating. So it's a continuous fight between what is condensates and it's at the same time evaporating because of that. So this specific, gas phase chemistry will be really dependent of the region in the solar system and particular time, because of this continuous influx of materials coming from the outer part of the disk. The reason for this infall of materials is because during the first 10 millions of years, you still have a lot of gas, but you have also a lot of materials, because all these condensates were falling into the ecliptic plane, and then you have collisions between the growing particles in the disk. Okay, there is a really significant paper by Kama et al. 2019 in Astrophysical journal that in fact was describing the different pathways of sulfur in different environments. In particular, in the interstellar medium, they indicate that most of this sulfur is in a diffuse phase, and also when they go, all this sulfur begins in the gas in the interstellar medium, but goes in protoplanetary disk, becoming more refractory. Most of this, in fact, is explained because of this behavior of highly siderophile of sulfur, so it goes closer to the metals that are condensing, iron-nickel alloys, mostly. And of course, the iron, remember the idea that you have materials that are going in towards the sun, increasing the temperature, evaporating, and you have, in fact, the primordial silicates were phosphoratic, rich in magnesium. But in the inner part of the disk was a really impressive processing of materials towards iron-rich, because iron oxide was in the vapor phase. So this iron oxide was also having a significant role in there, and can produce, of course, depending on the amount of sulfur in the gas phase, you have also the production of troilite or even pyrrhotite, no? in some aspect. So there is a continuous inflow of materials. This is the vaporization and sputtering of these materials in the inner disk is also explained as the source of the only phase that is most volatile, is the sulfur oxide. That they have observed, in fact, in protoplanetary disk as tracers of the stellar winds. And I think this is quite interesting. This is also a paper by Booth et al. 2018. But in general, and the part that I'm mostly explaining here is that sulfur also participates, is mobilized in the interior of carbonaceous chondrite asteroids, probably comets, under the action of aqueous alteration, because sulfur is very quickly mobilized and is producing sulfates in the interior of these bodies, as we also review in a Space Science Reviews paper. Okay, so the basic idea is this temperature profile. Depending on the distance to the sun, you have different materials that are condensing. Of course, this is affected by all this highly dynamic evolution of the protoplanetary disk. Concerning the chondrite groups, we are lucky to have really materials that have been mostly unaffected by thermal processes, so they were accreting into undifferentiated asteroids that never went heated so much. That will be represented in these petrologic types by the 3 petrologic type in this area. We also have some few ordinary chondrites that are really amazing. They are informing, even they are not so, in general, most of these meteorites are not so pristine because they have experienced thermal metamorphism, because they come from hundreds of kilometers asteroids. But they are few samples, like Semarcona, that are extraordinarily amazing for such type of, inspector observation of what was going on in these first stages. And in particular, I will deal with the 3 most highly acutely altered carbonaceous chondrites, the CIs that you know that are the most significantly acutely altered meteorites and are the closer composition to the sun. And the CM, well, CI is carbonaceous from Ibuna, the first meteorite in this group. In this case, we will also describe CM and CR chondrites that are experiencing really, everything is a little bit messy by the transformation from PowerPoint. I'm sorry about that. Okay, so concerning these components in chondrites, just as an example of things we are observing, and taking into account that these color images obtained in backscatter and with X-ray mapping analysis, magnesium, calcium, aluminum correspond to red, green, blue. RGB are magnesium for red, calcium green, and aluminum blue. So in here, for example, we can see a really nice aluminum-rich condyle in the interior of one of the most pristine CM-like. It's not a CM, but it's really close by a CM. It's one of the most pristine carbonaceous chondrites. You can see in here, for example, these purple things are calcium aluminum rich inclusions. And this is a very fine-grained matrix, and these are the so-called condyles, in this case, phosphoritic magnesium-rich condyles. At the same time, you can see, of course, the fine-grained matrix is what the way we are really interested in, to try to understand how all these materials that were affected by heat were chemically processed, in that sense. We can see in here, for example, an ameboid olivine inclusion. That's a kind of aggregates. And these materials is what we are particularly interested. Of course, we need to mention the significant role of these guys. In this case, you have a particle that gives us a clue about what was going on at the very beginning. These are the oldest condensates, oldest particles surviving in the protoplanetary disk. Not at all so different from the rest of the materials. In fact, there is a clear complementarity between the composition of the fine-grained materials forming the matrix of these undifferentiated meteorites with the materials that are forming condyles or other type of inclusions. The thing is that as you can see in here, this is quite amazing. You see that this kind of an aggregate is stuck to a particle that has been heated and overheated, probably very close to the sun. So the materials that were forming this particle were also chondritic in nature, were this type of materials. But because of the heat, at the end, the particles ended having these highly refractory phases. Spinel, magnesium, aluminum, oxygen, as you can see here, melilite, and carbonate. So in general, we can explain this by these processes that were going on in the very beginning. The amazing thing of these sea ice is that they contain a big variety of isotopic anomalies. They are rich in oxygen, aluminum, manganese, calcium, rubidium, that we suspect was inherited from incompletely homogenized materials. Just as a very fast overview, of course there is not much time, but in here you see the two types of conduls that we have in these undifferentiated meteorites. An iron oxide rich condul that in backscatter is, as you see, very close to the tone of the surrounding matrix, and a magnesium-rich phosphoritic condul that, as you can see here, is very easy to distinguish from the surrounding matrix. The difference between them is, in fact, this thermal processing, the fact that the particle that was melted from really microscopic or nanoscopic materials and made a rounded igneous spherule, a condul, okay, in the disk, if remained in an environment in which the iron oxide was particularly dominant, at the end, the magnesium-rich condul ends in an iron-rich condul. Okay? And of course, this also contains sulfur. In the sulfur in this particle, for example, is attached typically to the iron, metal grains, iron-nickel alloys that we can see in here. As you can see here, the metal in here is in the condul, but the materials that were overheated in the inner part of the disk, most of this iron, more of this metal, became oxidized. So they were forming part of the same silicate structure, and they are far brighter in backscatter, as we can see in this high FeO type 1 condul. Okay, if we look to the most pristine, from the point of view of the chemistry, the meteorites that are more close to the solar composition, and we can compare this as made Anderson Greves, 1989, the solar photosphere compared with the sea ice. You see that here is a very good match for most elements, except for some perhaps moderately volatile, like sodium, for example, and lead in here. So in general, we have these materials as starting values, no, for the solar system. In the literature we have use of the term of cosmic abundance of the elements. I won't say cosmic, but I will say that it matches solar composition. If we compare this composition, attention, this is the abundance of different groups, CMs, CBs, and ordinary chondrites. This is a work by Connell Alexander, 2007, et al. If we compare the abundance of these different elements depending on the 50% condensation temperature for each element, okay? obviously, if the material is like the sun, or we'll say Ci chondrites, will be in a line in here, okay, in 1. As you see, there is not the case, because for the CMs, CBs, and ordinary chondrites, we have different slopes. It's quite clear. Well, this points that there is an elemental fractionation in chondrite groups, indicating that the models, the ideas we have about the condensation, about the formation of these bodies, depending of the heliocentric distance, the distance to the sun, are correct. We have in these groups of chondrites different distances, sample, compositions for different distances, and probably different times of accretion. Okay. Carbonaceous chondrites are also really, really fascinating, because they can contain not all, but some of them have not water at all. They went dehydrated. But some of them can contain even a 12% in mass of water, and about variable few percents, up to 4 or 5% of carbon in mass. All the materials that were experiencing aqueous alteration were these groups mostly that I explained. And this went about processes going on concerning gigantic collisions over bodies that, in fact, were formed with extraordinarily high porosities. Porosities of the order of 70, 60%, 50% of porosity, because of the sticking of the materials one by one, and of course collisions participated in processing these materials, in compacting by the shock waves these asteroids, in the way that some of these bodies, the ices and the materials that were hydrated, finally got some temperature in the interior and were slightly cooked, okay, at low temperatures, but with enough temperature to make the water in liquid state, in a way in which this water participated in the alteration of the minerals surrounding the water, the regions that were hydrated. The most amazing thing of these asteroids is that we have clear evidence that the hydrated areas are not homogeneous, because the aqueous alteration will depend on the availability of water near the matrix, near the conduls, near the different inclusions that were in these meteorites. For large, relatively large bodies, like the body that is providing us the CM chondrites, we were studying the effects of aqueous alteration, and we find out that the CMs have different degrees of aqueous alteration. So they can have really fascinating meteorites, like Queen Elizabeth 97990, this meteorite I showed, the Foster D condor with the medal in the interior. But we have also a fall called Bacabel, and affected by terrestrial alteration, where you see that there is almost all the material that is, highly active in the interior, the metals, for example, just are gone. Were affected in the asteroid, in the parent asteroid, probably because different burial depth. So they were hydrated. The same happens with different fine-grained minerals produced by aqueous alteration. In some meteorites are very well preserved, can be observed. In others are gone, are like diluted in the matrix. In here you have another example, even for the silicates, those conduits that were not containing metals. Can be this possible because some conduits rotated and the metals were going out of the condule, you know? For these cases, we have CM chondrites with no metal, only the silicates, olivine, forsterite, but others that have been transformed. You cannot see big details in here. You have some remaining olivine grains, but in here you have mostly serpentine, phyllosilicates. So the water was transforming the condule in a kind of ghost of what was going on. For the CR chondrites, we have also evidence of really amazing chemistry. For example, the pyrrhotite is transformed little by little into this. This hole was a sulfur-rich pyrrhotite grain that, because of the water, was transformed in this really amazing magnetite cluster. So, as you can imagine, for us, discovering this is exciting. I won't say much detail of this, but I will inform you just briefly. Phosphorus. So most of these bodies providing CRs can be also fascinating, perhaps having clues on cryovolcanism or some kind of really extensive aqueous alteration, mobilizing many of these elements. Okay, going for evidence for wet accretion. You see here a condule with some kind of mantle. Look at this, it's sulfur-rich mantle that I will explain how this is produced. Because the condule in the outer part of the disk became having a nice rich mantle with sulfur-rich content. So when it introduced in the matrix of the meteorite, and realize that this is a very fine-grained meteorite. This is La Paz Icefield 02342. This is our paper in Nature Astronomy. You can see that the material, the water, when it's compacted, probably was the action of some temperature. The ice was, releasing the water, and the water was soaking the closer part in the meteorite. So the sulfur is mobilized few tens of microns. Sometimes 100 microns are surrounding the condule. This is a clear example of wet accretion in this kind of meteorite. Then we went over this guy. Yes, we discovered this clast in Barcelona, just looking by the petrographic microscope. I used to see in transmitted light, and when you have really some patch of carbon-rich material, you see that it's very, very red. And I went really surprised about this. You can see, you can compare this darkness in backscatter with the surrounding carbon-rich matrix. So it's really, really dark. And when you observe with different instrumentation, with the same red, green, blue, but in this case calcium, magnesium, silicon, calcium, sodium, silicon, you see that something really weird is in this meteorite. When We decided with colleagues in Carnegie, Larry Nidler, Rhonda Strout, and collaborators to study this really amazing material using nanosims. We discovered, for example, this is the cluster, a part of the cluster, not complete, a little bit is up. You see that the cluster, the xenolith contains hotspots of carbon-12, deuterium hydrogen, and even some small hotspots of what we consider an interstellar typical feature, the nitrogen 15 to 14. You see that there is clear evidence for different functional groups in the near-edge spectroscopy using chains. At the same time, we were studying the content in presolar grains because this is really exciting stuff. So you see that the cluster, in fact, is close related with the most pristine meteorites as well. I mentioned before this conduls in Astrophysical 094 in here. And you can see that there is even close correlation with some interplanetary dust particles that are really fragile materials. But when you look in close detail to the border of the cluster, just touching the matrix of the meteorite, you realize that you have this kind of different composition for the oxygen isotopes. Well, this really, as you can see, in here, the mapping, you have that the anomalous thing in here is that you have oxygen 16 poor grains in the upper border of the carbonaceous cluster. The same EDX maps in here are red are sodium, green is carbon, and blue is sulfur. You see that there is a clear tendency to have sodium-rich sulfates in these materials that are placing as well the composition of the material from the oxygen isotopic very correlated with the most pristine meteorites we have in our collections. Something happening here. So again, in here you see by using a STEM, scanning transmission electron microscopy, we were observing the cluster and just to find out the interconnection between the sulfides and the organic matter in the meteorite. In general, the maps are pointing to a connection between metal and sulfide grains. So again, we have this close correlation with the refractory phases. Just performing some cuts, you know, in these fifth sections of the cluster. This is part ongoing work. You see that we were identifying a sodium-rich assemblage that is containing also altered silicates surrounding, including clays, serpentine-like clays, and iron sulfides as well. Okay. And concerning the other types of minerals we can find is the iron-rich carbonates. It can be also interesting for you, the siderite-like grains with variable oxidized iron as well. So this is a kind of really diverse xenolith. So we are convinced that this xenolith came from materials available in the outer disk where Kuiper belt objects form. Remember that we have this geophysical model of Arrokoth by the New Horizons with really fluffy composition, about 70% of porosity estimated. that can be represented perhaps by this kind of materials in the other part. The lower deuterium-hydrogen ratio in the clast compared with organic materials in the CR chondrites and in IDPs and some extreme ultracarbonaceous micrometeorites may represent a temporal change in compositions of refractory organic matter. So everything was probably changing in this part of the disk. And of course, this can be affected by all these processes you were discussing, you were so nicely introducing concerning, for example, the ultraviolet processing of organic precursors that were probably affecting these kind of materials. So if we conclude that if such a temporal evolution in cometary deuterium hydrogen exists, it will be not surprising for cometary materials sampled by CR chondrites to be less anomalous, since these meteorites have the youngest accretion ages. That is also important. And of course, the presence of this clast in the interior of a meteorite, undifferentiated meteorite that was probably accreted not so far from the sun, but not so far, means that these processes I was mentioning you about fragmentation, about decay in the orbit towards the inner part of the protoplanetary disk were going on, and at the same time can provide us really exciting pathways about the delivery of these elements to the Earth. Particularly, we have the clast accretion, interstellar processing. We have evidence for gems, glass with embedded metal and sulfides, probably produced by the cosmic radiation as well. This clast, once was fragmented from the parent body, was moving in the protoplanetary disk, was initially sealed. It contained a kind of ice mantle, then formed an ultracarbonaceous body, probably an ancient comet. And when the comet disrupted, this small 100 microns clast went incorporated into the CR asteroid. So lab 02342 clast composition demonstrates that the outer disk had a very unusual gas phase chemistry at work, with ices and organics irradiated together with moderately volatile elements and creating complex condensates that we have never seen before in such a detail in most cases, and that of course are now focusing our attention. So as main conclusions, of course open to discussion, moderately volatile elements and on the other hand, sulfur, are depleted from the hot inner disk. Indifferentiated meteorites provide pathways to understand early processes at work in protoplanetary disk. And the discovery of this clast opens the doors in the search for other cometary xenoliths. And this authentic relic explains many things concerning the first accretionary phases of cometesimals and planetesimals. The rest of the content, I will say, is more than explained in the rest of the talk. So, thank you very much.
Yeah, thanks for the nice talk. So I'm really outside this field, so maybe my question will be quite stupid or so, but
No problem. We also learn from naive questions. And we have the same naive questions on your topic.
So if I understood correctly, so you can, depending on from where the chondrite or the meteorite is coming, you can see that. So if it was far away from the solar system, then, or in the outer parts of the solar system, it has a different composition, but instead if it's closer, so the composition is different. But how accurate can you determine from where it is coming? Because I guess you are determining this based on the chemical composition of the, so is this not still?
It's a good question. The thing is that it's really difficult to know exactly which is the formation location of this. For most of these carbonaceous chondrites bodies, we will say that the formation regions will be in the outer part of the main belt. So between 3 to 5, 6 astronomical units, in most cases. But of course, again, and the class that I describe is an example, you have a lot of fragmentation, mixing of materials. Long time ago, many colleagues of me were proposing, for example, Adi Bischoff, were proposing that the carbonaceous chondrites, these undifferentiated meteorites, were not the primordial bodies in the solar system. If we have the clear idea that perhaps the Kuiper belt objects, the trans-Neptunian objects, have so high porosity, fragility, they are like snow, even fluffy than that, no? So obviously, during the first 10 millions of years before, most of the gas in the protoplanetary disk was released by the solar X-wind of the sun, probably in such a period was a big mess in the entire solar system. So we have, at the end, we concluded with different rings, as also discovered in protoplanetary disk by ALMA, for example, recently. Different rings in which you have different dominant compositions, and of course also affected by a stochastic process, like a series-like body that goes close to another and just crashes in a catastrophic disruption and then brings to a specific ring or rings more materials that nobody was expecting to find. So many of these processes were completely stochastic. We know nowadays that the terrestrial planets are the product of tens of planetary embryos, if not saying hundreds. So of course, the remaining things, the remaining groups of undifferentiated meteorites are as well containing part of these processes, and then defining exactly, I will say, is so a big mess to try to do that.
I apologize in advance for the question, but
No problem. Well, contaminated from the point of view of, staying in the, is a very good question, staying in the terrestrial surface, and then in terrestrial surface, if we are not recovering the meteorite in few days, I will say hours, and really you got particularly the highly porous carbonaceous chondrite, hydrated, because they are absorbing part of the water. No, it's like they are just breathing in some aspect, and you can demonstrate that because if you made in a oven thermal step-by-step increase in the temperature, you see that you do that for a carbonaceous chondrite that has been in the Earth. With a very low increase in the temperature, you still to release water vapor. Well, in general, terrestrial alteration is highly oxidant. And you can realize that a meteorite is pristine, you have a recent fall, because you have almost no aqueous alteration of terrestrial nature, because aqueous alteration of terrestrial nature is producing iron oxides, limonite, that in fact is changing the appearance of the meteorite. When you make a thin section, you see that there is some orange stuff surrounding the metal, the native metal. So really you can find very, very quickly what is really pristine to what is contaminated in the sense of terrestrial. On the other hand, has been fully demonstrated over time, we were lucky to have two important faults, Allende and Murchison. In 1969, just when the NASA was preparing the Johnson Space Center. So these meteorites were brought in question of days to these labs and then demonstrate a very long argument of organic chemists about is this organic really asteroidal? And the answer was yes, because in fact the meteorite itself, if unaffected by aqueous alteration, there is not way to transfer this organic matter to the interior of the meteorite.
The time scale of these processes?
In general, the dating of the carbonaceous chondrite is of the order of 4,560 millions of years, more or less. The dating of is about 5 millions of years for accretion after the formation of condyles, or 7 to 8 millions of years after the formation of the calcium-aluminium rich inclusions, the CIs. So they are the primordial blocks from which terrestrial planets were created. That's a planetary embryos that at the end finish as terrestrial planets. Okay.
I hope probably the last question is, we have a debris disk where we have many collisions between grains and planetesimals. What compounds do you expect to see in gas phase? Well, I am probably molecules are destroyed, but let's say, what do you expect to see in gas phase?
Particularly, of course, all these highly volatile elements in catastrophic collisions of planetesimals, you have vaporization of moderately volatile elements as well, sodium, potassium, and other elements went to the gas phase. In fact, in the very beginning, the X-wind is throwing these elements very quickly, to the outer part of the disk where they are created with ices, forming cometesimals. A long time ago, we predicted that the comets were sodium-rich. And then Stardust mission on Churyumov-Gerasimenko demonstrated that Churyumov-Gerasimenko was sodium-rich. We did that by studying cometary meteoroids fragmenting in the atmosphere. And I made this during my PhD. And we discovered that the sodium abundance of these ionized columns were between 7 to 8 orders of magnitude higher than the abundance in the top of the atmosphere. So we clearly stated that the sodium was in the materials, and it was later explained in this way. So it's clear evidence for all these continuous processes. In a debris disk, as you don't have so intense solar wind, probably you will have also recondensation of part of these moderately volatile species, and perhaps you have a gas phase chemistry that can be also dominated with some of these elements as well. Like in a protoplanetary disk, in an early disk, I will say that we can observe a lot of magnesium oxide, because magnesium is dominant, iron oxides, this kind of molecules. Thank you.
Try to speak to see that we hear you.
Good morning.
Okay, it works. You can start.
So I share my screen.
Okay.
I try at least. Where? Share. And hello.
Will you see?
No.
Yes, we see.
Okay. No, I think there is an echo. There is a difference. Okay, I have an echo.
We can hear you quite.
I will close the YouTube. Maybe it's that. I don't know.
Ah, sí.
Okay, I start now. It's okay, like that. Hello.
Hello, do you hear me?
Yes, and you.
Yes, perfect.
Okay, I will start. So good morning, and excuse me if I am not in person, and okay, it's for several reasons I could not come. So I will present an overview of what we know about sulfur in comets, especially about sulfur-bearing molecules that we observe in the comet atmosphere. So next slide. I don't know how I go. Okay. So you know, I am sure that comets are quite interesting in the context of understanding the star formation processes, because this body formed in the outer solar system, and they did not evolve since then formation, and especially we have a lot of evidence that they were not reprocessed, for example, by the circulation of liquid water in their interior. And in addition, with respect to the meteorites and asteroids, they have ices, so they provide also information on the volatile content of the protosolar nebula, and of course on the sulfur species in this early solar nebula. So they provide clue to the solar system formation, of course, but also to the origin of the volatile in the telluric planet, and also on the composition of the planetesimal which formed the planets. So about the composition of the gas phase of the volatile species, this composition is studied mainly by spectroscopy, so either infrared spectroscopy or radio spectroscopy or UV spectroscopy. And you see here the number of molecules which can be remotely detected, especially with the IRAM 30-meter telescope as a function of time. Now it's quite easy when a comet is arriving to detect about 10 to 15 molecules in this comet. So this occurs about one time per year. I show you here some spectra. I will not show you so many spectra during this presentation, but these spectra show a first detection in comet Albob, just for illustration. And you see, for example, the SO and SO2 lines. And this was the first detection of SO and SO2 in a comet. And this was in comet Albob, because comet Albob was a very productive comet. And in this comet, we identified a lot of molecules, organics, but also sulfur-bearing species. So the composition of comet is studied in general by spectroscopy, but it has been studied with also from spacecraft, like the Giotto spacecraft. We fly by comet Halley, but more recently, it was this composition was studied by Rosetta, and especially a lot of new molecules were detected by the neutral mass spectrometer on board Rosetta, and also these sulfur-bearing species, which are given here as smelly molecules. And okay, but I will talk in more detail after about these new detected species. So this slide show you a summary of the molecules which were detected by spectroscopy, so essentially from ground base observations. And so you see they are organized by organic molecule, nitrogen-bearing molecule, and you see all the sulfur-bearing species which have been detected from the ground. And so you have H2S, which is the main species, OCS, SO, SO2, CS, H2CS, and NS. And also S2, which was detected by in the UV, in fact, in several comets. So you see in the right, you have the number of comets where these species were detected. So you see that most species were detected in several comets. In addition, this plot is not do not reflect actually the number of comets where this molecule have been detected. And so what you see here in blue is the range of abundance which have been measured in the comet. So what you see here is also that the abundance, in fact, vary from comet to comet. There is a diversity in the composition of all molecules and also for the sulfur-bearing species. So here it's another way to plot this abundance. And so, in fact, in the ice, cometary ice, water is the main component. It's about 80% of the ice is made of water. You have the nitrogen species about 1%. The organic molecule is about 4%. The hydrocarbon is about 2%. And the sulfur-bearing species is about 1%. And you see also in this plot that H2S is the main compound in average, and then you have OCS, SO, and SO2. In fact, okay, I try to go to the next slide. Okay, in fact, what I show you, this plot is for the mean abundance. But if you compare from comet to comet, in fact, you see, you measure that the S over O ratio from comet to comet vary in fact from 0.5 to 2%. So you have really a diversity, and even in some comets, H2S is very depleted and is not the main sulfur-bearing species. And so in some comets you have other species like OCS or SO which are more abundant than H2S. So this, what I said for the moment was about the results we got from spectroscopy, and especially from radio spectroscopy. And the view changed quite a lot thanks to the measurements which were made by Rosina, and this neutral mass spectrometer on board Rosetta. So you have the same kind of plot, but from the result from Rosetta. And what you see here is that, in fact, atomic sulfur appear to be a major component of the gas phase volatile species in comets, in fact. And of course, this sulfur species was not possible to detect it from the ground. And So with Rosina, we, of course, the molecules which were also detected previously by spectroscopy were detected, like SO2, SO, OCS, H2CS, but other molecules which were not detected by spectroscopy were newly identified. And so these molecules are quite poorly abundant, and it's one of the reasons of why they were not detected in radio spectra, for example. And among them, you have methyl mercaptan, I think, CH3SH, which is quite a minor component of among all the sulfur species. And so other species, one interesting species which have been detected is CS2, because CS is detected from radiospectroscopy, and it was supposed that in fact CS was a photodissociation product of CS2. CS2 is not observable from the ground. And so the detection of CS2 in fact confirms that at least part of the CS that we very easily detect in comet is coming from CS2. So another species which was confirmed is S2, and also some organic organosulfur species were detected. So they are listed here, which are CH4S2, C2H6S, etc., etc. So as far as I know, the abundance of these quite complex sulfur organic species were not measured for the moment, because you need some calibration of the instrument for this species, and this is not yet done. So I will continue on this result. So in addition to S2, as you will see, I will talk more about, also S3 was detected and S4 was detected. This is the elemental budget which was obtained thanks to the Rosina data. So it's a quite complex plot, but I will try to explain this plot. So what you see here, all these points in black, so this provides you the sulfur to oxygen ratio determined as a function of time. So you have here measurement with Rosina from May to August 2015. So this elemental abundance in black, this point, is based on the sulfur molecule which were detected. So you see some variation with time, but overall these variations are not so important. And you have in orange, in fact, the photospheric abundance, so what we call the cosmic S0 abundance or the solar abundance. So you see that the elemental abundance in the volatile is lower than the sun abundance. But you have to take also into account that a comet is not only made of ices, and of course you have dust, and the dust in fact in mass is more important than the ice in mass. It's at least the dust to ice ratio in comets is at least 2, and even there is a lot of discussion about that, but could be even 10. So if you take into account that you have some sulfur in dust, and if you take the ratio sulfur to oxygen, which was measured so in the Halley dust, and also in the samples which were returned by the Stardust mission, in fact you obtain this yellow, no, not yellow, purple line. So you see this, which is just above the photospheric value. So overall, the elemental abundance of sulfur in comet is quite consistent with protosolar value. So you have also in this plot the value in chondrite. So this is the black, so the black line, the one which is on the top. And in fact, so you see that this value in chondrite is higher than the values that you observe in the photosphere or in comet, and this is because, in fact, in the meteorite, you have a depletion of oxygen with respect to the sun, which is not observed for the comets. So it's why you have this high sulfur to oxygen value in chondrite. This is due to the depletion in oxygen. Okay, so I continue, and so some remark. So the first remark that I can make is that, in fact, it was possible to measure the H2S abundance from radiospectroscopy in comet 67P during its 2020 apparition. And so it was interesting because it was possible to compare it to the measurement made by Rosina. And this is important because for most comets, in fact, the H2S abundance is measured from radio data, from millimeter data. So it's very important to compare to the Rosetta data. And in fact, so you see, I show you here, so these observations which were made so in November, December 2020 with the IRAM 30-meter telescope, and they were possible, and because the comet was quite close to the Earth at this perihelion passage. So it was at 0.4 astronomical unit from the Sun. So it was possible to detect H2S, FCN, and also methanol and other species. In fact, in the millimeter, 8 species were detected. And so you have in the right, in fact, in axis, yes, in x-axis, you have the abundance measured by Rosina, and in the y-axis, you have the abundance which were measured from the millimeter. And you see that in general, for all the species, you have a relatively good agreement, but this is not the case for H2S. And in fact, the H2S abundance measured by Rosina is from 10 to 20 times higher than the value that we measure with the IRAM 30-meter telescope. And for the moment, we have no way to explain that. It's not a problem of our model of the excitation of the rotation line of H2S, and so we have no way to explain that. And so this is an interesting point to investigate in the future months of year. Okay, so I go to my next point, if I can succeed to the next slide. Okay. So another interesting point is the fact that SO, so sulfur monoxide, is present in nuclear ices. And in fact, the previous observation made by, for example, the Plateau de Bure observations, in fact, in comet Albop, we obtained maps of SO2 and also of SO. And we were not able to reproduce the spatial distribution of SO by the photodissociation, just considering the photodissociation of SO2. And in fact, this interferometric observation were suggesting that some SO was produced by the nucleus. And so that this is a very good news that effectively Rosina confirms that you have some sulfur monoxide, which is in the cometary ices. And also in some comets, we found from the radio SO abundance, which was higher than SO2 abundance. So it was not possible to argue that SO was produced by SO2. So this is a very important result from the Rosetta mission. Another important result from the Rosetta mission is that there is a large amount of sulfur, which is in form of atomic sulfur, and possibly in the ices. So the question is, can atomic sulfur survive in the ice of comets if, for example, this sulfur is produced by the radiolysis of the H2S ice for example, in the protosolar nebula. Now I will talk about the sulfur elemental abundant in 67P, just a few words. This sulfur elemental abundance in the dust has not been measured in 67P. I do not know the exact reason, because it has been measured with the Giotto, so I don't know why. There is probably some instrumental reason. But what we think is that the sulfur in the dust, in the refractory material, is in the form of sulfide. And this sulfide, in fact, the presence of sulfide are highly suspected, in fact, to explain the fact that the comet material is very dark. The albedo of the 67P surface, for example, is about 5%, and you cannot explain this albedo by just considering that you have a lot of organic material in cometary dust and in the cometary nucleus. So you need some darkening agent, and in particular sulfide, to explain that the very dark cometary nuclei. Now I will come back to the volatile component and about CS. So I told you that the identification of CS2 by Rosina was a good news to explain why we are detecting CS in cometary atmosphere. But in fact, we have several evidence that CS is not coming uniquely from the photodissociation of CS2, but is also probably produced by the degradation of the dust grains. So one of the results first that I will show you is a recent observation with ALMA of so this was in comet in this comet 2015 ER61. So you have in the up in the left the ALMA map of HCN line. So this was the 4-3 line, and in the right you have the ALMA map of CS. And what you see here is that the CS is more extended than the HCN, and as the lifetime of CS2 is very short. In fact, we would have expected a CS map, CS extension, which would have been about the same as the HCN extensions. And so you have in the bottom, in fact, an analyzing of this map, but this time using the visibility, because it's easier to get some quantitative estimate of the extension of the molecule if we are working in the UV plane. And so you see in the left, you have the HCN visibilities of this line. So this is plotted as a function of the projected baseline, of the antenna baseline. And so you have these blue points, and these are the measurement. And you have the curve in red is what we expect for a parent molecule distribution. That is, if HCN is obtained is released from the nucleus. And so you have in fact a nice fit. So HCN is released from the nucleus. But if you compare look to the plot on the right, so you have again the measurement, which are this blue dot, and the parent the curve that we would have expected for production from the nucleus is this line, which is a dashed red line, and you see that we cannot explain the observations by a release from the nucleus, and nor by the release by CS2, which is this also this dashed this dashed line in black, and so the best piece is obtained for a distributed source with a scale length in the coma, which is of about 2,000 kilometers, scale length of production. That is, in average, the CS molecule would be produced in this at this distance. Okay, so now, so this was for the map. Sorry, I am last. And we had another evidence. So this is based on numerous observations of CS in comet. In fact, if we plot the CS to HCN production rate ratio measured in comet as a function of heliocentric distance, so you have this plot, and so it's a lot of comets. You see that the CS to HCN ratio increased when the heliocentric distance decreased. And this can be interpreted by the production of CS by the degradation of some organic material, or at least some material which is on the grains, and this material it would be very sensitive to the temperature of the grains and would decompose when the temperature of the grain is higher, that is when the comet is closer to the sun. So this is another evidence that CS is produced also by the degradation of grains in the atmosphere of the comets. And in fact, we observe the same for HNC. In fact, HNC, so we have the ALMA maps of the HNC special distribution of comets, which shows that HNC is produced by grains in the atmosphere. And we have also a measurement of HNC in many comets. And we see also in comets that the HNC to HCN abundance is increasing when the comets are observed close to the sun. So it's about the same for CS and HNC. We have the same observational evidence that these two species are produced by the decomposition probably of some material which is sensitive to the temperature. So I know now I will talk about this species S2, S3, S4. So S2 was detected by UV spectroscopy with relatively abundance with respect to water. It depends about comets between 0.001% to 0.2% relative to water based on spectroscopy. And S2, S3, and S4 were detected by Rosina. So you see on the right, in fact, a mass spectra. So this is a work of Calmonte 2016. In fact, in this paper, you have a summary of all the most results obtained on sulfur-bearing species with Rosina in Comet 67P. So this, you see this nice mass spectrum with the detection of S3 and S4 and S2 were detected, and you have a determination of S3 to S2 abundance of 3 and S4 to S2 abundance of about 1. So the point to know is that this species, S2 and especially S3 and S4 species, are very refractory, not very, but quite refractory species, and they sublime at temperature more than 280 Kelvin, so they are released from the dust particle, from a warm dust particle which are present in the coma. So the origin of these species, I think there have been laboratory measurements which shows that these species probably were formed by the radiolizing of H2S ice, either in the solar system protoplanetary disk or in the interstellar medium, in the presolar clouds that form the solar system. In this paper, Calmonte et al., and this is argued by Catherine Albeck, they are arguing the fact that if we have S2 present in comet, this is arguing that S2 was formed in the presolar ground, and that the grain containing S2 in the presolar cloud did not sublime in the solar nebula before being incorporating into comet, and their argument is that the S2 has a very short lifetime. Effectively, at 1 astronomical unit, the lifetime of S2 and is 100 seconds. And so due to this very short lifetime, any S2 formed in the solar nebula would have been destroyed. So it should have been formed before the formation of the solar system. So this is argued by Catherine Albeck. So now I will talk about isotopic species, measurement of isotopic species related to sulfur. So you have here a nice summary. So this is in a recent paper which is available in as a forthcoming paper in astrophysical and astronomy. And this paper summarized not only present new measurements of the D/average ratio in hydrocarbons, but also present a summary of all these D/average measurements measured in cometary species and also in the refractory species in comets. And so you see something that you know, certainly know that the D/average ratio in water in general in comet is relatively enriched with respect to the D/average that we measure in Earth's ocean. We have a high enrichment with respect to the protosolar nebula value, which indicates that this water in particular formed by chemistry at very low temperature, at least was the subject of isotopic fractionation at very low temperature. And what you see here is the D/average ratio in H2S, and in fact it has been measured. In fact, the HDS to H2S ratio is 1.2 plus or minus 0.3 10 to minus 3. So this corresponds to a D/average ratio of 6 10 to minus 4. So it's also a high enrichment with respect to the Earth value, and of course with respect to the protosolar value. So it indicates that H2S was a topic of deuterium fractionation at low temperature, such as the mechanisms which are proposed for interpreting the enrichment, deuterium enrichment in interstellar source like protostar. Okay, so this is the average ratio in H2S, but we have also measurement in sulfur. So the isotopic ratio, sulfur isotope have been measured, observed, detected in comets. From the ground, it was possible to detect, for example, C34S in the radio. So you see here the detection of C44S in comet Lovejoy together with CS, and this was a quite active comet. Of course, it's only possible in quite active comets, but for the moment, with radio spectroscopy, we do not have the sensibility to detect small variation that are expected for the sulfur isotopic ratio. And what we can just say is that the ratio are consistent with the solar value. On the other hand, from Rosetta, thanks to Rosina, it was possible to get much more sensitive measurements for 34S, and also it was also possible to detect the 33S counterpart of the H2S, CS2, and OCS molecule. And so I will show that in the next slide, but you see in the bottom, in fact, some mass spectra, and you can see, for example, in the plot in the middle, the detection of H233S, or a peak at the mass of H233S, or a peak at H34S, or peak at H234S, etc. So this show you the detection of this species. So I will show you the measurement after, but about this sulfur isotope, it was also possible to measure the abundance of 34S in the stardust samples of comet Will 2, and also in the 67P dust sample, not sample, but in the 67P dust. But the precision of the measurement is not so high. I will show you. And at least for 67P dust, it was found to be consistent with the cosmic solar, that is the solar value. So I show you a summary in the next slide of this sulfur abundance. So this plot can be found so the left plot can be found in the paper in the Annual Review of Astronomical Astrophysics made by Catherine Albeck. And so the last plot show you. So this is an information about the depletion of 34S in the different material. So this is the notation which is used by the people who are analyzing meteorites and IDP, etc. So it's not directly the ratio between the isotope abundance, but it's a deviation with the ratio of the Earth, with respect to the Earth. Anyway, if you have a negative value, if you have a zero value, it's the Earth's value about, which is very close to the solar value. And if you have a negative value, this means that you have a depletion in 34S. So you see on the left, all these black points is those obtained from radio spectroscopy. So you see that we do not have the sensitivity to measure the small deviation which are expected. And after you have this square this square point, which are the Rosina value measured in the gas species. And so you see this small depletion in 34S. You see that for the 67P dust, so this is a star, red star, so we don't have a very precise measurements. We see that for comet Will 2, the value which was measured in the dust is equal to the cosmic value, but that for a dust particle returned by stardust, we have a very different. Also, we have a depletion, and what is interesting is that this depletion in 34S are quite similar to the depletions that we found in pre-solar grains. So I don't know if the process is the same, but in pre-solar grains we observe in a depletion in 34S, and this is explained by the fact that these pre-solar grains were related to form, in fact, was a result of supernova processes. So we don't know if this is the process that can explain this depletion is the same as is meaning that we are incorporating comets incorporating some sulfur which were formed in supernova events. So you have in the right, in fact, it's the same kind of plot, except that in this plot, not only we plot the depletion in 34S, but also the depletion in 33S, because we also, with Roninas, they measured also depletion in 33S. So you see here this red dots are the measurement in the CS2, OCS, and H2S in the comma of 67P. And so you see this depletion in 34S and 33S, and which are similar to some depletions that we can find in the, so these are this light purple square that we can find in pre-solar grains. Okay, so I will finish my talk now. So this is the last slide of my talk about the oxygen isotopic ratio, which were measured in sulfur-bearing species. So it's again, of course, it's again a measurement by Rosina, and so in this plot, in fact, it's in the left plot, it's a summary of the O16 to O18 measurement in molecule measured by Rosina. So you have in this plot, of course, H2O, O2, CO2, CH3, OH, and also formaldehyde, and also the measurement which were done in SO, SO2, and OCS. And what is interesting is that there is a depletion in O16, in SO, SO2, in OCS. That is an enrichment is O18 in sulfur-bearing species. And so it's a very significant depletion with respect to the sun value, and also with respect to the value which is measured in the Earth's ocean. And this enrichment is 18O is apparently can be explained with gas grain chemical model. So this has been done by Loison et al. It's a paper published in 2019, and they are able to explain this enrichment is O18 thanks to the an efficiency in the exchange reaction between O18O and SO. and so this is good to know, and because there are other measurements, in particular in isotopic isotopes, measuring cometary molecules, which also are consistent with a chemical model at cold environment in interstellar, like prestellar course. On the other hand, we have to remark that this model does not predict any significant sulfur fractionation as measured in molecules, in cometary molecule. So I will finish here, and in this talk, I did not make comparisons about the abundance of sulfur-bearing species with interstellar source, and this is because this is, in particular, this is the topic of the talk of Maria this afternoon. She will talk about that in detail, and so the story will continue this afternoon. Okay?
Thanks, Dominique. So, time for questions. I'm afraid that you need to come here to make your question, because it's the only way that Dominique can hear you.
I do not hear you very well.
Yes? Well, I am very close to you.
Yes, so repeat the question.
Wait, where are you? Because I have, well, okay.
Can you hear me, Dominique?
Yes.
Yes, so thank you very much for your nice talk. So I would like to ask you, so you demonstrated that the CS has an extended origin, and it probably comes from dust, if I understood properly. Are there other sulfurated molecules that should be also the same origin, or it has only be done on CS?
So about the molecule which are coming from grains, so we are fully 100% sure for HNC, for H2CO, for CS, and of course there are actually there are a lot of discussion about ammonia, because with this detection of ammonium salt, they could be also, this ammonium salt could be also responsible for the production of some ammonia that we observe. This was your question?
That was my question, and it was also the possibility to be related on salt, but you mentioned it, so that was my following questions, but you answer both, so it's okay. Yes. Thank you very much.
After, because for example, we have H2CS in cometary ice, but this H2CS cannot explain neither the CS we observe nor its evolution with heliocentric distance. So I think it's strongly support that CS is produced by grains, and we had this nice observation, ALMA observation by Nathan Roth, which clearly shows that yes, something is happening for CS, something strange.
More questions? If you want to stop share your screen, Dominique, then we can see you directly. Well, I have a question about the, probably it's not for you, it's for Jean-Christophe Loisson, about the 18O over 16O, because you explained as a consequence of the reactions of SO and 18O. I don't remember, but you have also the same ratio in formaldehyde. And formaldehyde, well, there is not an obvious connection between formaldehyde and SO. But I suppose that this is more a question for...
I do not remember if the model of Loison is able to explain the ratio observed in H2CO. What is very important there is that the O16 to A18 ratio measured in H2CO is not the same as methanol. So the H2CO and methanol, because it is often proposed that H2CO is formed by, I don't know, oxygen or addition of methanol, so this is a byproduct. But here the different isotopic ratio shows that the two species are not linked in comet, and we know that most of the H2CO is not present as H2CO ice, because we know that for this molecule, a large part of this is produced by grains. So it's, I don't know, polymer, or I don't know, some kind of strange material, organic stuff. You see, it's so.
Okay.
But it's complex, and the isotopic ratio in refractory organic material is quite complex, because you have all this, the history of the organic material in the solar system, and yeah.
Okay. Well, one question more. Maria is coming.
Maria has a question. Well, she knows everything.
Yeah, hi Dominique, thanks for the talk. More a comment. So about the oxygen isotopic ratios, the comparison I would say maybe take with a grain of salt, because the comparison is being done to gas phase isotopic ratios, and I think in the solid you may see slightly different ratios. I know it's a gas grain network, but the published isotopic ratio for the gas phase. So I'm still curious exactly what they will see in the solids, which I think will be a closer comparison for the cometary values, because I think the interstellar ice will be a closer comparison to what we're seeing in cometary nuclei. So I would say we need to take a closer look at this a bit more, and then I wonder to what extent this disagreement between formaldehyde and methanol will still stand.
Thank you. Any other question? Okay. Thank you, Dominique, for this interesting talk.
So I will connect through YouTube.
Okay.
Okay.
Bye.
Bye.
So I will get started. This is going to be possibly a bit of a jump in terms of a talk with respect to the previous ones, because up to now we have been seeing mostly the data that build up into the planets, so the planets of the solar system, the asteroids and comets as their building blocks, and this talk is going to be more a perspective talk, so how can we apply what we know from the solar system and all astrophysical sources to understand exoplanets. And basically, the big challenge that waits us in the coming years is that of understanding what the large amount of data on exoplanets and their atmospheric composition we will get first from the JWST and then in a few years from the Ariel mission will tell us about how this planet form. And at the moment the problem is that we have tools to connect this atmospheric composition to the formation history of these planets, but these tools are not as refined as we would want. They mostly deal with only two elements, carbon and oxygen. And as we will see, and partly it was already introduced by the previous talks, carbon and oxygen are very reactive elements, so they can take a number of forms within this and then end up in planets through different means. So what we need to build in the coming years is a reference interpretation framework for exoplanetary atmosphere and generally planetary atmospheric composition that connects it to the formation history using as many elements as possible so that we can frame the problem from multiple points of view. And because the subject of this workshop is on sulfur, I will highlight what sulfur can tell us that we don't get from other elements. And why do we have this problem of connecting the atmospheric composition to the formation history? Basically, this starts when we compare, this becomes evident when we compare the information we have from exoplanets, the solar system, and circumstellar disk about where planets are. And this basically tells us that the planet formation region in disks is much larger than even the most optimistic theoretician thought up until a few years ago. Basically, in disk, what we see are the signatures or possible signatures of planets, because there is a bit of debate still, that extend to tens or even hundreds of astronomical units from the star. So planets should be able to form even at these large distances because we see them. But when we look at exoplanets, 75% of them are on orbits that are closer than that of Mercury to the Sun. So a fraction of astronomical unit. And in between we have the solar system where we see planets that span from 0.3 to 30 astronomical units, plus the possible planet 9 at 200 AU. That's the last estimate. So wide range of formation regions, or at least a wide range of places where we see planets. Even if we account for biases, that means that planets should be able to form over 3 to 4 orders of magnitude of distances from the star. And this is not just a problem of where the planets form, because when we see exoplanets, and when we see them mostly as transiting exoplanets, so objects that are very close to the star, and we see passing in front of the star, and we can study them during these passages, we don't know where they came from. If we have such a large planet formation region that spans basically the whole extent of the protoplanetary disk and all its compositional regions, when we see a transiting planet, are we seeing something that formed locally in the outer region of the disk? Are we seeing something that always form from the colder regions, like the one we see with ALMA, and they migrate to where we see them? Or, because of the migration, we see a mix of different compositional regions, so we don't see a clear signature. There have been studies until now that try to deconvolve this problem, so using the features of physical and compositional characteristics of exoplanets to understand where exactly in the wide expanse of protoplanetary disk and all the compositional regions the planets form. The first idea was to link the planetary metallicity, or the density, depending how you prefer to think, to their migration history. Basically, early studies, a few years ago, studies started doing population study of the metallicity of planets based on the mass and the measured radii, using equation of states to connect them to the metallicity. And what you see is the top plot. So you have the planetary mass and the metallicity. There is a decreasing trend of metallicity for more massive planets that we see also in the solar system, as Luisa was introducing today. So we have Jupiter that is more metallic than Saturn, that is more Jupiter is less metallic than Saturn, that is less metallic than Uranus and Neptune. And we see these also in exoplanets. But the other point, the striking point, is that basically all these exoplanets tend to have superstellar metallicity. So they are more metallic than a star. And the idea is, okay, if the planets migrate, because these are mostly transiting planets, because if we want the radius, we need to have the possibility to measure it during the transit. They encounter material during their migration, they accrete the material, puff, we get the metallicity. However, this works in principle, but things are never so easy. So we have a huge uncertainty in this very connection, because we don't know the characteristic of the disk that generated the exoplanets when we see the exoplanets. The disk is long gone at that point. So we can have a massive and extended disk, or a less massive but more compact disk, and we can have a planet that have the possibility to encounter the same amount of material with different migrations. Even if we have just one disk that fits all the exoplanets that we see, so all the exoplanets forming in disks that are basically similar to each other, we have other degeneracy connected to the formation track. This is a plot of the mass of planetesimals that Jovian planets can capture migrating from different distances, so from 50 AU to 20 AU from the star down to 0.5 AU. And you see, basically, intuitively, the more it migrates, the more material it will encounter, the more metallicity it can get. But if you take this planet and you change the migration time scale, you see that you change the amount of captured mass. So basically, the same planet starting at 20 AU, if you make it migrate faster or slower, you can mimic forming at 30 or 10 AU in terms of metallicity. And you have a number of snow lines in these regions. So the composition that produce that metallicity is not going to be the same. So yes, you can get an information from that, but is not necessarily a very constrained information. It mostly tells you how much material it encountered rather than how much it migrated. Even before the idea of the metallicity, however, there has been the proposal using the C/O ratio, the carbon over oxygen ratio of planets. And basically, you can see in the top plot, let's see. Yes, a remake of the original plot by Oberg et al. In 2011. So in purple, you have the C/O ratio of solids. In green, you have the C/O ratio of the gas. And you see this nice increasing trend of the C/O ratio of the gas. So if you have a planet that captures only gas and not solid, because, for example, your disk is populated by dust, and when the planet reaches a giant planet mass, it doesn't accrete the dust anymore. The higher your C/O ratio will be, the farther away from the star you will have fallen. The C/O ratio of the solid is going to be substellar, and it's going to decrease at the beginning with distance and then start to increase, which already introduced a degeneracy in the problem, because in principle, if you mix half of material captured in this region and half material captured in this region, you can mimic a planet that formed this region. In principle, you can deconvolve this with the metallicity, so this will be a low metallicity and these are higher metallicity planets. So in principle, you can break it down, but if you take the most up-to-date information about the partition of carbon and oxygen between meteorites and comets in the solar system, and you match it with also information about oxygen in planetary material in polluted white dwarfs, elements in circumstellar disk, etc., and you mix everything, what you get is that you probably have something like this instead. So you start with a very small C/O ratio. There is a decrease when you have the snow line of water, but then if you get refractory organics in the game, you jump immediately almost to the stellar level. So you can have a C/O ratio that is different from the stellar one for solids only in a region that is a few AU, because In the solar system, it is thought that refractory organics survive until about 5 AU from the star. So it's not a very wide region if you compare it with the fact that we see planets at tens of AU, and they could, in principle, migrate close to the star. And the gas loses this nice monotonic trend, but oscillate around the values that is roughly twice the stellar value. That's just assuming the simplest possible scenario for the disk, just updating the values and the partition with the most up-to-date information we have. The other problem is that this simple scenario is the one of chemical inheritance, where the volatiles come from the molecular cloud that give birth to the star and the disk, and you have a low level of chemical activity, for example, due to ionizing radiation, cosmic rays. In this case, you see that you have regions where your abundance of solid increase, and these are basically the snowland that we know. However, if you change your disk to something with higher level of chemical activity, and possibly the fact that the disk was reset, for example, by an outburst of the star during episodic accretion, because the star is not just a source of gravity, but is an object that is evolving at these stages, you get something much more complicated in your disk. And you lose the information on the snow line. For example, if you look at water, this line, this dark blue curve, you see that we have a peak, a spike, then a decrease, then what would appear as a snow line, another decrease, and another snow line. So we lose even the concept of snow lines that we think of. So what we try to do is, okay, let's try to complement information from carbon and oxygen with other elements. That's the work that we've been doing in the Planet Formation Working Group of the Ariel mission. And the elements with which we started playing are nitrogen and sulfur. Basically, the reasoning is that we want elements that have different volatility from oxygen and carbon, both higher and lower. Nitrogen is more volatile than oxygen and carbon. Sulfur is more refractory. Doesn't matter at this point if it is refractory or volatile or whatever. It's just that it is more refractory, so it's a comparative line of reasoning. And you can see this argument basically if you compare the abundance of meteorites, the CI meteorites that we were seeing this morning, and they are the red dots here, with the proto-sun abundances. And you see we have a good match. There is a depletion of oxygen by about a factor of 2 between stellar abundances and CI abundances. Carbon is present only 9% roughly in meteorites with respect to solar abundances, so it is more volatile than oxygen. Nitrogen is present only at 3% level in CI meteorites, so 97% is not in the rock phase, but in more volatile phases. So it's more volatile than oxygen and carbon. Sulfur basically matches. Actually, if you compare the meteoritic abundance with the solar abundances, there is slightly more sulfur in the CI meteorites than in the sun, but that's probably a calibration artifact. So sulfur is more refractory, so it's present in rock components in more abundances than oxygen, carbon, and nitrogen. Is this valid outside the solar system? Because here we're using the meteorites, which form in a specific disk around a specific star. Well, again, this plot was introduced already this morning in the talk about asteroids. We have evidences from protoplanetary disks around stars more massive than the sun, B stars, that about 90% of the sulfur that is accreted on the star comes from refractory phase. So again, the refractory phase of materials, rocks in our case, and metals, should account for roughly 90% of sulfur. And if you take the data that from comets that were introduced in the previous talk, and you try to mass balance them with the sun, with the fact that generally those abundances are scaled to the abundance of water, they are not absolute but relative abundances, and you do some games in the mass balance, you find out that also in the comets in the solar system you have roughly 10% of the sulfur in the ices. Can be 20, can be 10, but most of sulfur is refractory. So what you do at this point is that you take all this information, you try to build your compositional structure for the disk, where you consider the different elements like chondritic rocks and metals, then you add water, refractory organics, ammonia, CO2, CH4, And in principle, if you have a colder disk, you will have also CO and then 2 in the solid phase. The disk we were using to start is not this cold. And you put this into a model of planet formation where you have the seed of your giant planets starting at a given position, growing in mass and radius. You can see the growth of the mass and the radius here. So at the beginning, you will have an extended phase of atmosphere, where the planet has a giant atmosphere and a core that is forming and creating the gas. And then there is going to be the bump of the runaway gas accretion when the planet reaches its final mass and the core and the radius compacts to become that of the giant planet. You put this into an n-body simulation with a disk, you trace the evolution, and you compute your flux of planetesimal, which is the blue curve that you will see here. The orange one is still the mass, it's just a linear scale. This one is the orbital radius, so the planet is migrating inside. You get the information of how much material you capture by the planet, your metallicity, but you also get the information on the mix between different compositional regions that you get into your planet. And the important takeaway from this animation, when we reach the last moment, is that you see that the different regions in the disk will contribute differently, but in some cases comparably between each other. So what you get is a non-stellar mixture. Basically all the models of planetary atmospheres for exoplanets that we have to date generally assume stellar mixture, or solar mixture if you assume a solar analog of the star, a solar analog for your star, which is what most work do, because the sun is the one for which we know the composition best. They just scale the metallicity rigidly, but if you increase oxygen by a factor of 3, in these models you will have also carbon and nitrogen enriched by a factor of 3. But what this plot is telling us, this animation, is that this is not the case. You will not have nitrogen, oxygen, carbon, and sulfur in stellar balances, which changes the chemistry of your atmosphere. So what happens into our planet? Okay, I hope that you can see it is not very contrasted, unluckily. What happens basically is that while there is a connection between the elemental ratio of the planet to those of the disk, they are not the mirror image of one of the other. Basically, you have 2 examples of planet. One are creating only gas, like for example, it is the first object to form in a disk that is still gas and dust, no planetesimal to impact on the planet. And here we have planetesimal that impact on the planet. For example, in our case, we will see C over this one is the nitrogen over oxygen value. The green one is the C over O, carbon over oxygen. And then you have the carbon over nitrogen value. And you see they deviate from the stellar. Okay, an important thing about this plot I will show, because the elemental ratio have different absolute value, you cannot easily compare them. So the trick is you normalize them to the stellar abundances. So basically, these are normalized ratio. If you want, they are relative enrichments. So C over N, the normalized C over N ratio is how much enriched is carbon with respect to nitrogen in units of stellar abundances. And you see there are trends. For example, the C over N ratio is substellar, which is what happens also in the C over N ratio of the gas in the disk. The lower plots are the elemental ratio in the disk. N over O is superstellar in the gas of the planets, and that's the case also in the gas of the disk. Similarly, you have substellar N over O in the solids, substellar N over O in a planet that accretes a large amount of solids and gets heavy elements from solids. So there is a match from the qualitative point of view. But as you can see, for example, the N over O ratio of a planet that is highly metallic decreases with distance, while the one of the disk increases. S over N increases and is at the maximum closer to the star. But if you look at the orange curve, the red curve, the S over N of planets forming closer to the star decreases. Each point is a planet, identical planet, a Jovian planet, starting at different distances. So 5, 12, 19, 50, 100, and 130 AU from the star. That's because is not just a sum of the material, but it's also weighted by the efficiency with which the planet captures material in a specific region. So it's basically a summation with weights. And you need to look at the composition through the lenses of planet formation. You cannot just map the composition of the disk into the planet, that of the planet. That's the main point. What happens if we change the chemistry of the disk? Because at the beginning, in the previous slide, you were seeing the same disk and you were just changing the planet the formation track of the planet. So where it starts and what it accretes, only gas or gas and planetesimals. If we change the chemistry of the disk, we see two things. The ratio that do not involve oxygen, S over N and C over N, they are basically the same. Here you have the different color indicates chemical inheritance, blue color, red color is chemical reset. So the disk underwent an outburst and you restarted the chemistry from scratch in the pressure and temperature condition of the disk. The triangles are for high chemical activity and the circle for low chemical activity. And you see S over N, the trend is basically the same. There is a limited effect of the chemistry of the disk. C over N, the same. If you have a gas-only planet, you have the same trend for all the disks, this chemical scenario. If you have a planet with high metallicity and they're creating a lot of solids, you have the same trend. We move to the trends that involve oxygen, and it becomes a bit of a mess. You see that, for example, the reset scenario, the red one here, deviates significantly by a factor of a few from the inheritance scenario. If we look at the C over O ratio, we see that for gas-only planets, they actually invert. An inheritance scenario will produce, as expected, C over O ratio in the planets that are superstellar, but if the disk is dominated by chemical reset, the C over O ratio is going to be substellar, which is what prediction were assuming is what happened if the planet is a high metallicity planet accreting on planetesimals. So you have a degeneracy in interpreting if you don't account for the chemistry of the disk. And also, well, if you know about this, you can use this to get information from the planet about the disk it was born. If you only trust oxygen-based ratios, you have to break down a certain degeneracy that is not easy, necessary to break. Sulfur, as we say, has a trend that is basically independent on the chemistry of the disk. That's mostly because it immediately goes into solids, into rocks. So the chemical evolution of the disk that affects mostly the ices doesn't really affect sulfur that much. As we saw in the comets talk earlier this morning, there is a fraction of sulfur that goes into ices, so there will be a small effect, but it's going to be a second-order effect. And the interesting thing is the sulfur over nitrogen ratio mimics the metallicity of the planet. Basically, the farther away your planet starts, the higher the metallicity will be, but also the higher the S over N ratio will be. If you start very close to the star, S over N will be substellar, metallicity will be substellar. But that's only the metallicity accreted by rock material, planetesimals, comets and asteroids. Also, the gas will bring some metallicity, and if you form very close to the star, you will accrete little planetesimal, basically because you encounter less mass in your migration, and the gas will provide you some heavy elements that will be comparatively as large as those you get from planetesimal. That's why the total metallicity is larger than the one you get only from solids. This is actually interesting because the fact that the S over N mimics the metallicity of solids, that for large-scale migration is basically the same as the metallicity of planets, tells you that if you can measure, if you have two estimates of the metallicity, S over N and the traditional one from the mass radius relation, if the two matches, you have an indication that your planet started very far away. Its metallicity is mostly due to the accretion of planetesimals. If the two diverge by a factor of 2 or more, then what it is telling you is that your planet got its metallicity both from the gas and the accretion of planetesimal. So you can deconvolve the source of the metallicity thanks to the S/N ratio when you compare it to another estimate of the metallicity, like the mass-radius relation. And this is basically due to the fact that sulfur is refractory or works like a refractory element for our purposes, so it traces solids. Nitrogen is an ultra-volatile element, so it traces gas. So the S/N ratio can be used as the S/H ratio. So basically it gives you something that approximates the total abundance of sulfur, and therefore you can use it to trace the total abundance of refractory elements, hence planetesimal that you accrete. I showed you before that we were playing with a number of elemental ratios. There were 4: carbon over nitrogen, carbon over oxygen, sulfur over nitrogen, and nitrogen over oxygen. What happens when we put them together in the scale? You already saw this in the previous plot, but let's pay a bit of attention now. If you pay attention to the colors, what you notice is that planets getting their metallicity from the accretion of planetesimals, and giant planets getting their metallicity from the accretion of gas only, have inverted colors. Basically, if you look at a planet and you can measure this elemental ratio, if you see that the N over O is greater than the C over O, that is greater than the C over N, you have a planet that accreted only gas. If you have the opposite, C over N greater than C over O greater than N over O, you have a planet that accreted both gas and planetesimals. And interesting enough, even if we published 1 year ago this new method for the Ariel mission, it has been already tested by one work by our group and another work by an independent group. So we have a total of 8 planets, and basically we have 4 following this path and 4 following this path. Sulfur, if you look at the plot, seems to basically follow the C over N ratio. Doesn't seem to be giving you a lot of information, because basically what from these trends you can tell from C over N is the same that you can tell from sulfur. Does it mean that sulfur doesn't have any other use? Actually, no. If we look at the same plot in a linear scale, because the other plot was in a logarithmic scale, so everything was squashed down. So if we look at a linear scale, you can see that because sulfur is more refractory than carbon, if you have a flux of planetesimal, they will bring proportionally more sulfur than carbon. Hence, the S over N ratio will grow faster than the C over N ratio with migration. So if you find yourself in this situation, where S over N is greater than C over N, you can tell that your source of metallicity is planetesimal only. If you are instead in a region where the C over N is greater than the S over N, you know that you had some contribution of the gas to the metallicity, because the gas also brings carbon, it brings much less sulfur or no sulfur at all, and therefore the gas doesn't compensate the lower accretion of planetesimals. So sulfur will decrease faster when you get less planetesimal than carbon, because carbon will be compensated by gas. It looks like it is a limited shift here, and it is telling you the same as the metallicity plot that I showed before, but in reality this allows you to discriminate between 2 important planet formation scenarios. Because up to now I've been talking about the planet accreting only planetesimal, which is, if you want, the standard scenario that has been around ideally from the early ages in which we started studying how giant planets form. However, recently, works focused mostly on the chemistry of disk pointed out that if you have disks that are rich in dust, and the dust drift together with the gas toward the star through the mass accretion rate of the disk, the dust will cross the Nesno lines. The ice on the dust will evaporate and will go back to the gas phase. And this process basically will enrich the gas. So for example, inside the Nesno line of CO, the evaporation of the ice will bring carbon and oxygen in the gas. And this can bring your gas to become superstellar in metallicity. So you get a gas that is more metallic than the original gas of the disk. This process depends on the accretion rate on the disk. You have 2 examples here that for some reason you cannot see. Basically, this is a stronger transporter, so you have a stronger flux toward the star and a more limited flux toward the star or gas. And the difference is that if you have a stronger flux, you get basically an homogeneous enrichment throughout all the disk. For example, if you look at water, this would be the level of the normal abundance of water, but the transport brings it up by a factor of a few. Same as, for example, CO, that should be here and jumps here, CH4, from here to here. If you have a slow transport, you don't have this diffusion effect, so you will get bumps locally inside the snow lines. So depending on the scenario, you can get a big enrichment of the gas, so a planet that accretes gas can have high metallicity and still not accrete planetesimals in this scenario, which means that you can end up having a planet with high metallicity, which you would think accreted planetesimal during the migration, and instead it didn't. It's just gas. In this case, you will burst the abundance of carbon, you will get higher CO/N ratio. This process doesn't affect sulfur, so your S/N ratio decreases, and you will end up having your curves in this regime. So if you have a high metallicity, but you have C/N greater than S/N, that's a clear signature that this planet accreted enriched gas and not planetesimals. So basically it becomes a probe into the details of the mechanism of giant planet formation. So I already put a lot of different ideas on the table and touched a number of subjects. So I think I can close here and just leave you with the question that you have been asking ourselves in the Ariel working groups, which is, in these models, we made a certain number of assumptions that are reasonable about the starting condition. For example, we put all the sulfur in the refractory phase. However, we saw there is a fraction that goes into ice. How much is it? Is it 10%, 20%, or the range can be higher? This sulfur that goes into ices, is it going to stay in ice form, or is it going to change? We saw in the talk about comets that there is the evidence of S2, S4, S3 molecules, so chains of sulfur atoms, and that can be the product of radiolysis of ices. Is this process effective enough, for example, in some circumstellar disk, for example, due to the radiation of surroundings the birth cluster of the star and its disk, to change a large fraction of the sulfur from ice to refractory phase? Because this also affects how efficiently sulfur is trapped by the planet. And finally, and this is something I regret not being able to follow yesterday, but I will catch up with the recording. Do we have reliable networks to model the gas and the gray chemistry of sulfur? Because one of the things that we are thinking is we want to put stop reasoning only in terms of static disk or planet formation as something separate from the evolution of the disk. We need to consider the planets in the framework of the evolving disk and the revolving star. So the idea would be to couple disk evolution models and giant planet formation models and planetesimal formation models, and therefore we need to basically couple the time scale of the different processes. And one of the problems is how sulfur gets reprocessed before you freeze it into the planetesimals. I saw somebody going, no, when I asked if we have a reliable network, so I already got my answer. Okay, so, and with this, I leave the floor to question, comments, or things that are unclear.
So have you considered, or are you planning on repeating any of these simulations with, say, the pebble accretion model of planet formation?
Yes, but the problem with pebble accretion is generally that there is no unequivocal definition of pebbles, because some models consider pebbles that are basically the dust we see in circumstellar disk, so small size, like sub-millimeter, Other models focus mostly on pebbles that are meter or above, so like small planetesimal. And the two have different prediction and different effect. We are working to, for the moment the simulation I show are agnostic to the specific way we form the core of the planet, because we're using parameterized curves that mimics hydrodynamic simulation for the formation of the planets. We took them from planetesimal accretion, the classical core formation scenario, but basically if you take a pebble accretion, the curves are similar. So it's a self-similar problem from the point of view of the growth of mass. We are going to implement now equation for the treatment of pebble accretion. We will start with the small dust, so the one that is strongly coupled with the gas. Because that's the one that we see in circumstellar disk, a simulation of evolution from the prestellar phase, core collapse, down to the disk suggests that the size you get is sub-millimeter, so that should be a reasonable starting point. In the future, we will probably try also with larger pebbles, but for the moment, no, simply because of manpower. The critical aspects from this is the time scale on which you convert the pebbles into planetesimals, because this is what freezes the chemistry of your disk. So the indication are that in 1 million years, you should already have a population of planetesimal. We get this both from circumstellar disk and meteorites in the solar system. So the idea is, whatever models we assume, there should be a decrease in the pebbles in the first million years and an increase of mass of planetesimal. But this is going to be a parameter of our studies.
Okay. I was just wondering because I knew that the pebble accretion models tend to be really effective at getting water down to even terrestrial planets, and so that would potentially boost the O.
Yes, yes. That is basically, we have our PhD student, Elenia Pacetti, which was the second name on the first slide, that basically is doing this, is coupling the disk evolution models with chemical evolution models, and the idea is to estimate this effect. At the moment, we will start exactly with the small dust, so the small pebble regime, because it's the one that is simply easier to implement into also the N-body code. So we can have the same physical prescription in both the chemistry and the N-body part. But yes, basically that's an effect. I can tell you that from those 8 planets for which we saw the trends that I showed, we do have some evidences that while the bulk of the metallicity either came from gas or planetesimals, even for the planetesimal, there should be some effect from the pebble evaporation. So even when they were forming, most of the mass of solid should have been in planetesimals, because that's the dominant effect, but there was still a significant mass in pebbles that were accreting the gas. So that's absolutely something that should be put inside.
Okay, thank you.
Well, congratulations for the talk, very interesting. Just from my point of view, I clearly think that you are right concerning the sulfur abundance, elemental abundance in CI chondrites, more in front of the new data on Ryugu. Because we discovered on Ryugu that is not containing sulfur, is depleted in sulfur. So probably this makes sense in the, from the point of view that our CI samples, the meteorites that survive of CIs, that you probably know that there is a significant bias in the survivability of these really fragile meteorites. Probably these CI chondrites are heavily aqueously altered. So as consequence of this aqueous alteration, remember, for example, metal grains I was explaining in my talk are directly connected with sulfides, and under the action of water, these are highly reactive minerals and are very easily mobilized through the body, in the sense that you have that little by little, if there is enough water and this water percolates into the matrix of the body, at the end you have a lot of sulfates
In fact, in 1 cm chondrite, we discover a flow of sulfates produced by the action of water. So it's just try to fit all this, but makes full sense what you are saying of incorporation of sulfur in ices. Under some heat, this ice, mostly water, goes into the parent body, you know, and produces all these reactions that are changing the chemistry, the elemental abundance in the interior of the body.
Okay, that is good to know because it means that one of the assumptions is not crazy. Basically, when we did this work, we did one trick in reality, because when you, if you go down to mineral composition in meteorites and comets, as we saw in your talk and also the one on the comets, you have a richness of molecules. Tracing everything is beyond what we could do. So what we did is that we focus instead on the elemental abundance. So the basic assumption is once a certain fraction of the element is inside the body, we don't care in which phase it moves, as long as it doesn't move from rock to ice, in which case it's more tricky. But if we have the opposite, from ice to rock, that's perfect. So we were focusing on the elemental abundances, how they increase, because that allowed the problem to be more easily treated. Our understanding was that this should have been reasonable, but it's very encouraging that we see that the process is moving things from, if you want, from ices to refractory organics or more refractory material that survive until closer to the star. Because in the end, if we make an error in the innermost 2 or 3 AU, is less critical, if you want, because there is less mass and only planets forming closer and migrating will be affected, rather than if we have something that is wrong across most of the disk. Mm-hmm.
This becomes, by the action of water, as I saw this kind of transformation of the pyrolyte grains into magnet-like clusters. This, obviously, the sulfur is going into the matrix and producing sulfates, not sulfides, because that refractory particles.
Okay, perfect. That is something that we'll have a look into.
Thank you. This is, I don't know, in this kind of model, when you have migrating planets, obviously there is a dispersion of planetesimals, and this for certain will modify if further accretion takes place at different distances.
Yes.
And this can get a different, let's say, final view of the enrichment of heavy elements.
Yes, basically, if you look at the colors distribution in the first panel, it becomes more, you will see it, for example, if you trace the red, you see that you start to scatter them. And basically, what you end up is that after the first planet form and migrate, really after the first massive planet forms, the composition of the disk will be mixed, even if you don't have migration in reality. If you have migration, the effect is stronger, but even without, basically, think of Jupiter with the comets. Jupiter is basically transferring objects from the outer solar system to the inner solar system, and decoupling them and scattering, increasing the inclination, the eccentricity, and sending the comets closer to the Earth. In the disk, when you have a much larger mass of planetesimal, this process is order of magnitude more efficient. So just the formation of a giant planet will scatter material around. We have some simulation, basically, in which we can see that planets at 50 AU can send material that is original from 40 to 60 astronomical units inside the 10 astronomical units. Then we don't know where it ends because that's where we put the limit of the resolution. So basically, the assumption that the disk has a compositional gradient is valid only until you form the first massive bodies, or body. One planet is enough to make a mess, as you see here. If it is migrating, all the other planets, we see a disk that is completely different in terms of remixing. And interestingly, all these bodies that are on high eccentricity, this is semi-major axis and eccentricity. So these will be highly eccentric bodies, exocomets, if you're thinking in terms of exoplanets. They will cross large expanse of the disk, and basically they become high-velocity projectiles for all the other planetesimals. And then you get collisions, and then you get mass production, and then you get mixing of materials, exactly like we saw for the solar system with the meteorites. The presence of elements that are from protocomets or outer solar system injected into your rocks. So basically, the mixing is inbuilt into planet formation. And that's the reason why we started basically with only one planet, because the moment you put the second one, it's more complicated to understand, because basically this plot will become even more deviating from the stellar composition. So probably we expect a second generation planet will be even less stellar in composition and more unique. That's why we want to have multiple elements. Now we're considering sulfur, we want to expand the things beyond sulfur, because we need more details in order to match everything.
We can move to the next talk, because we are a bit late for lunch. And we can discuss more with you during lunch. Okay. Do you hear me?
Hola, Asunción. ¿Me oyes?
Sí, te oigo. Hola. Okay. I think you...
Yo te oigo.
Carlos is here and Cristobal, just to present something on the photodisruption of sulfur species, because you gave me this title. And it's like, but Asunción, I only have the case of...
Ahora viene.
Okay.
Okay. Everything is ready. Start when you want.
Okay. Buenos días.
In English. Oh.
I would like to... I'm online. Yes, Asunción.
Yes, you are online.
May I start?
Yes. Go on. Oh, sorry, because now it's very. Yes, you can go on. We are hearing you.
Okay. Vale, muchas gracias. I would like to present today about a work that we're doing, mainly focused on brown dwarfs. I may be the only one talking about this kind of objects. I'm learning a lot in the workshop about the different type of astrophysical objects and the chemistry. For us, this is quite new because, as I will show you, sulfur had not been detected in brown dwarfs, and just now we're starting to get some information, and it's just kind of the beginning for us working in this field. This work I'm doing with a PhD student in the first year, Yunjan Jerry Sang, and we have a collaboration with the chemistry department at the University of La Laguna with Professor Pedro Esparza. And at the IC, we work with Felix Gracia and Jose Luis Rasilla, who are in the instrumentation department, and they take care of the laboratory measurements of spectra. And from the theoretical point of view of simulating spectra, our collaborators are Thomas Masseron at the IC, Julie Gordon and Robert Hargreaves in Harvard, and from the astrophysical point of view of observational spectra, we have Nicolas Lodieu. I will give you a little bit of general context because I think it's good that you are a little bit familiar with what kind of objects we are dealing with. The brown dwarfs are sort of fail stars. They do not stabilize on the stellar main sequence. When they are very young, such as, for example, in the Pleiades cluster or even younger clusters and associations, they can be as hot as the coolest stars, the latest M dwarfs, with the temperatures around 2600 Kelvin. Then as they age, they cool down because their core is degenerate, so they keep shrinking, and they do not have a stable thermonuclear fusion for a long time. So they keep shrinking, they keep cooling, and then we have developed new spectral classes called L and T and Y, and that's where we are at the moment, but I will tell you about possibly a new, later, a new spectral class that we may need in the future. So brown dwarfs, well, to define some limits, they are objects that are formed like stars, but they are not stars, and they have masses at the substellar mass limit, which is the limit, the most massive a brown dwarf can be without becoming a star, and that's about 75 Jupiter mass for solar composition. And then the limits between brown dwarfs and planets is more fuzzy. In the literature, you can find that sometimes it's used the limit for deuterium thermonuclear fusion, which theoretically it happens at a mass of around 13 Jupiter mass. So the brown dwarfs and the planets overlap in the properties. We are interested in to study different molecules in the atmosphere of brown dwarfs because there are tracers of what the initial composition of the brown dwarf was at the origin, and they tell us about the history of the brown dwarf, and they are also tests of the predictions of models of the atmosphere. So in this workshop, I realized that it's a little bit funny that brown dwarfs, in some aspect, they are a little bit like a picture of what a protoplanetary disk has in terms of the range of temperatures that are involved. So to draw some analogy, the young and hot brown dwarfs will be like the inner regions of a protoplanetary disk with the temperatures of more than 2000 Kelvin. Then the intermediate age brown dwarfs, they cool down and they are like, you may think, the temperatures that are a little bit farther from the disk. And then older brown dwarfs, they get to temperatures close to the ice line and beyond the ice line. So actually here we have kind of an analog of objects that go very slowly during the lifetime through all this range of temperatures, showing us the change in the same object. So we think at constant chemical composition, but evolving very slowly and showing us how the properties are changing in a slow motion as a function of mainly the temperature. So we can see that in the warmest brown dwarf, the spectrum is dominated mainly by oxides like titanium oxide, vanadium oxide, and in the coolest M-type, we start to see the signs of formation of refractory material. Dust condensation, we see it because we start to see that these titanium oxide bands are weakening with cooler temperature instead of getting stronger. So this is interpreted as the effect of the first dust grains condensating in the atmosphere and drawing mainly this the most refractory material, such as in this case titanium. Then when we go into the L class, we're sampling a range of temperature between 2200 Kelvin and about 1000 Kelvin. Then we see a strong hydride, for example, iron hydride, but then also we see it gradually disappearing, and this gives us information also about the kind of refractory material that is forming and condensing below the photosphere. And as we go to the LT transition, that's a very interesting region which is poorly understood. We think that there is the transition that the main carbon-bearing species is going from CO to methane. We see also that the dust grains are becoming larger and they are sinking. So we see that the atmosphere is getting more transparent. We see that the water is getting stronger. The water was already present in the L class at hotter temperatures, but in the T class it's getting stronger. And then in the coolest brown dwarfs, the so-called Y type, then we start to see the presence of ammonia, which is already present in the T dwarfs, but it becomes more conspicuous in the Y dwarfs. Basically, there is a smooth transition between the T and the Y. The Y class, because it's so faint, is relatively unexplored at the moment. So this is sort of the sequence of spectral types and temperatures, and you can think of it as a sequence of age in a given object, which transitions from a very young age of, say, the age similar to the protoplanetary disk, 1 to 10 million years, then it's very warm. Then at the age of a few 100 million years, then it becomes intermediate temperature, and then by the age of the sun, the objects are with the temperatures getting close to those of the planets, the giant planets such as Jupiter. So these isolated brown dwarfs are analogs to planets, but they are easier to study because we don't have the glaring effects of a very bright nearby star. There has been several comparisons in the literature. I just put you here as an example, the recent paper led by Hervé Bouy, and where we can see low resolution near-infrared spectra of one object in the Upper Scorpius OB association, which has an estimated mass of 6 Jupiter mass. So it's like a very young brown dwarf at age of about 10 million years. Compare here with a white companion to a brown dwarf, which was discovered about a decade ago by Chauvin and collaborators, this 2MASS1207b, and also one of the objects in the planetary system around the bright young star HR 8799. So you can see that the spectra are quite similar at this modest spectral resolution and signal-to-noise ratio. But it's just to give you the message that the brown dwarfs can have analog spectra to objects that are in orbit around stars and that we may call planets. Our previous experience in this field of research is coming from a different science goal. At the time that Luisa Valdivielso was doing her PhD with us, we had in mind the possibility of making gas cells in the near infrared mainly to improve the Doppler precision in order to find planets around brown dwarfs. So that's when we started to collaborate with Pedro Esparza at the chemistry department of the university, and also with some colleagues in the US. So in that paper, our goal was different to the one I'm presenting today. Basically, we were mixing different gases inside the cells in order to try to provide as much of forest of absorption lines in the near infrared in order to serve as reference to compare with the spectra at high resolution of brown dwarfs. So here we have an example of a combination of gases that we made in the laboratory. And we took the spectrum here above. Maybe you can see my cursor. And well, we found that this was quite a good match for reference to the spectrum of a warm brown dwarf, in this case an M9 spectral type. And well, here for reference is the telluric spectrum in the region. So we could see where the best windows of the Earth atmosphere were for the Doppler information. Actually, this kind of work was very interesting, but then the new instruments had developed another method, mainly based on Fabry-Perot-Étalon, and this method of the gas cells has been put on the side. It didn't go very much further than that. So our current work is based on trying to understand the spectra of brown dwarfs and changing the spectral resolution from low resolution to high resolution. Of course, the low resolution is what we get for very faint objects. We cannot do much better than that. So we are interested to extract the information even from low spectral resolution. So for that, our three pillars are to have our in-house laboratory spectra with some limitation. They are reliable because we know what gases we are putting, but right now we're limited to working only on the room conditions of the laboratory. We don't have the capability to go to warmer or cooler temperatures or higher or lower pressure. So this we compare with simulated spectra to check the completeness of these simulations. Of course, this has the advantage that with the simulated spectra, we can then simulate different kind of conditions. And then this we compare with observational spectra that we have or we can find in the archives or we're planning to get. These are some of the team members. So here, starting from left to right, you can see Jerry Sang, the grad student. You can see Pedro Esparza, the chemistry professor. You can see Araceli, who was an exchange student who came for a short time. And you can see Felix, who is the expert of the optical laboratory. And he's showing one of the gas cells that we are using and which are made in the laboratory where Pedro is working. So very recently, we published this paper as a letter in Astrophysics, showing some of the laboratory spectra and how they could be compared with low resolution observational spectra. And also we show that this has a very good potential for in the near future the hundreds of thousands of low resolution survey spectra from the Euclid Space Mission. So in this paper, we show our ammonia and methane laboratory spectra. We compare with the simulations. We found that the simulations reproduce some of the strong bands, but some of the weak bands appear to be missing. Now we understand that the problem of that comparison is not coming from the HyTran database. It's coming from the software that was being used to extract information from the database, and that software was missing some of the information on the weak bands. So now the simulations that we have in collaboration with the Harvard people are much better than, especially for the weak bands, than it was when we did this work. So we use that to optimize spectral indices that can be used for spectral classification of brown dwarfs, and we also derive a molecular ratio of ammonia to methane in the atmospheres of brown dwarfs in the latest T types and the Y types at low spectral resolution. So we compare that with the model atmospheres, and we found that there is a generally good agreement with the expectations from models for solar composition. So we think that, well, as expected, these nearby brown dwarfs, they all have similar chemical composition to the Sun. This is still unpublished. This is something that we are doing at the moment. So we are trying to quantify the lack of methane in a very interesting object. I cannot really tell you much about it because we are working on a press release about an accepted paper, so it's sort of not at the moment. I cannot really tell you much, but this is something that it was quite a surprise to us because we found that there is an object which was discovered a few years ago, and it has strange colors. So we started making an intensive monitoring program of this object, and we found that it's about 3 times closer to us than it was thought. So it's within 10 parsecs. And we think it could be metal poor, but we still don't understand what it is. The spectrum is the bottom one. So we think it has a temperature similar to the spectrum, which is just above it. But you can see the spectrum is very, very different. And in particular, for example, you can see this very strong, this is our laboratory spectrum of methane. You can see, for example, this transition, very narrow, very strong, which is clearly seen in the T dwarfs, but is not seen in this weird object. So we think somehow methane should be there, but it's not, and we are trying to understand what's going on with this strange brown dwarf. So, but now focusing on the topic of this workshop, recently we have become interested in trying to detect sulfur in these atmospheres because it gives information about the atmospheric composition, about the network of chemical reactions, about the structure of clouds, and also about the processes of forming solid particles and raining them out below the photosphere. Some models, for example, those of the by Morley and collaborators, they have predicted that hydrogen sulfide should be one of the molecules that we should see in the spectra. And for example, here you can see the predictions for the molecular hydrogen, for methane, for ammonia, for water, and for hydrogen sulfide. So in red is the hydrogen sulfide. So usually it's below the other molecules. But here, just in this little peak here, there is a very narrow window where the model predicts that it may be actually the strongest absorber at that narrow window. And that's pretty much the only one in this range of wavelength. So actually, I was hoping to present you today the first detections of hydrogen sulfide in brown dwarf atmosphere, but we were just scooped a couple of weeks ago. This paper came out in AstroPH. It's a very nice high-resolution spectra from Gemini South, E-Green's high-resolution spectrograph. The paper is by Megan Tannock and collaborators. So in this, it's an shell high-resolution near-infrared spectrograph. And in this order, they are focusing in this narrow spectral window that I told you before that we were focusing. And actually, they do find this narrow spectral feature, which they attribute to hydrogen sulfide, and right here is the strongest one. They show that it's quite convincing, the detection of this feature due to the hydrogen sulfide. Well, it's a bit surprising that because the object is, they estimate a temperature of about 1000 Kelvin or a little bit warmer, maybe 1100 Kelvin. And for that temperature, the predictions were not that the hydrogen sulfide will be dominating here. Actually, the predictions were more than water, ammonia should be stronger, but surprise, even for this warm object, they are able to find this dominating spectral feature. So hydrogen sulfide, as you know, has been detected also in this spectral window in Neptune and Uranus, in two papers by Irwin and collaborators. They also use the same spectral window, they model these transitions. So the fit without the hydrogen sulfide gets worse, particularly at that spectral transition. So it's really a very sharp transition where hydrogen sulfide is dominating. So coming back to our laboratory spectra, so the resolution that we can get in an efficient way, you know, like of taking measurements in the lab in about 1 day or so, they have the modest spectral resolution of 1250, but that's usually what we get in brown dwarfs. This Gemini south spectrum I show you is really kind of an exception. That's 40,000, but you can do that for not so many objects. So in our work, we are focusing in modest spectral resolution, and so far we are collecting a spectra of the main molecules and also the deuterated version of the molecules. So in particular, this is the window again. This is now looking at our laboratory spectra. So here in blue, we have water. We have ammonia in yellow, and we have methane, and we have this sharp feature that we also see in the laboratory spectra, and this is the one that we're focusing on. Our Harvard collaborators have been able to model the spectrum in one of our absorption cells, and they found that in that particular measurement, 95% of the absorption comes from hydrogen sulfide, and we only have 0.2% of water and 5% of HCl. So it's mainly due to H2S. And indeed, this feature is fully attributable to H2S. So we start comparing our laboratory spectrum for different molecules with spectra from the archives. So in particular, this is archive spectra from RTF for Jupiter, Saturn, Uranus, and Neptune. And we do see this sharp feature in all of them. It's more difficult to see it in Jupiter, but we think it's present there in also in the integrated Jupiter spectrum. And in the T dwarfs, we also see it. We see it even in the earliest T dwarf, and also in the mid T dwarfs and in the late T dwarfs. So this feature seems to be present in all the T dwarfs that we are looking at. In the metal pool, this very strange object, WISE 1810, we are not sure yet, because the quality of the spectrum, there may be something there, no methane, but here, this is our methane laboratory spectrum. This is the hydrogen sulfide spectrum. So this sharp feature is this one. The scale is not great. And here in the intriguing object, we may see something, but it's not convincing. There could be something, but the quality of the spectrum is not good enough. And here there is a stronger transition. There may be something, but again, I think we will need a better observational spectra for this object in order to see. And because this object has temperature similar to T dwarfs, but does not have methane that we can see in the near infrared, we think maybe in the future this can be a benchmark for a new spectral class that we may call the H dwarfs, dominated mainly by the water. Water we can see clearly here. This drop here is entirely attributable to a water vapor. So what the prospects that we have is to keep building a spectral library, which in the future we would like to make it free access. So far we are only doing stable room conditions, something that maybe in the future we can think of expanding a little bit. And soon we will have a new instrument that we are part of the consortium of the science team, and this will be Miradas at the GTC with a resolution of about 20,000 at near infrared wavelengths, and it's a shell spectrograph. And also in the near future we will have Euclid with the near infrared spectrometer that will take a deep survey in the near infrared at low spectral resolution of about 300, and we expect to have an enormous increase in the number of T-dwarf spectra from that, and then we can explore a wider variety of conditions in terms of the chemical composition of the objects. So that's it. Thanks a lot.
Thanks, Eduardo. Questions for Eduardo? I think we are very close to lunchtime. Now people is a bit tired. Only one short question. Are you able to quantify the amount of H2S relative to water in brown dwarfs?
Not yet. It's,
okay.
That's something we need to work on. No, at the moment, no, I cannot. Relative to water, you say?
Yeah. Well, I think this is the simple way to do that, no? Because you have a lot of water.
Yes, yes, certainly. We have information about water. We have information about methane and ammonia in the same object. So in principle, we can get estimates for that.
Okay. So thank you very much again, and also for the information of the new instruments. That I guess that will be very important also to study exoplanets and protoplanetary disks, perhaps.
Yes.
Okay.
Yeah. You're very welcome, and thanks a lot for this workshop. I'm really learning a lot from it.
Okay, we will keep in contact, Eduardo.
Okay.
Okay, so now is lunchtime. on. We are starting the afternoon session, and the first speaker is Roman Legal, that is going to talk about the chemistry in protoplanetary disks, in special the sulfur chemistry, of course. So, Roman, you can start.
Okay, thank you very much, Ascension, for the introduction, and also thank you very much for allowing me to present some results today. So I'm really sorry to not be there in person, but I hope I can come soon to visit you and all the team. So yes, today I'm going to talk about sulfur chemistry in protoplanetary disk and the recent studies that we have been doing, in particular when I was working at Harvard University, and I'm now working as a CNAP assistant astronomer at IPAG and IRAM in Grenoble. So we already heard a lot during these days about protoplanetary disk, but just to resume a bit why these stages are important. So we think they are important because they are pivotal stage in the evolution from interstellar molecular cloud to a planetary system, where everything starts at the molecular cloud stage and will eventually form a planetary system. And with the recent facilities that we have access to, such as radio interferometer, and in particular with NOEMA and ALMA, we are now able really to resolve those protoplanetary disks and to zoom into them to really study their structure in detail, so both the dust and the gas. And but there are still pending questions about those objects. And in particular, we still don't know what is and how the chemistry is influencing on the planets that are going to form in this disk. And in particular, so the sulfur chemistry is still veiled in those disks, and we still don't know what are the main sulfur reservoirs and what is and their distribution throughout the protoplanetary disk, which are also called now planet-forming disks, because we think that there are probably much more planets hidden in this stage already that we thought before. So, but just to step back a bit and to resume what we have so far about sulfur chemistry. So if I didn't forget any new detection or miss any new detection, there is 40 sulfur-bearing species that have been detected in space so far. So there are a wide variety of them, so ranging from 1 atom to more than 6 atom molecules. Sorry, I don't have my pointer here. I don't see, you see my mouse, I can point on the screen, but they are also varying from atomic sulfur up to more than 6 atom molecules. And there are, so in total, about 15% of all the chemical species that have been detected in space that are sulfurated. So among the 250 species that have been detected in space so far. What is also very interesting about sulfur chemistry, as you mentioned also yesterday, Ascension, is that they are observed in a wide range of astrophysical objects, so from extragalactic sources to our own solar system. They are commonly used to probe also physical conditions, so very precise physical probes, especially for shock, infall, or accretion, for instance. And as you also mentioned, they are very important component in the formation of life building blocks and in planet habitability. And this has been especially revealed during the past 5 years by especially astrobiological studies, as listed at the end of my slide. And among these 40 species, 6 of them, the one in yellow here, have been observed so far in disks. And what we can also note is that 4 of them have been observed very recently, especially thanks to the high sensitivity and high angular resolution of NOEMA and ALMA. So CS and SO have been observed more than 20 years ago, and part of them were observed by Assumption in the past. And then with the new facility we have access to now, we are able to observe 4 more. So H2S and C2S were observed with NOEMA in 2018 and 2022, so it's very recent. And SO2 and H2CS have been observed with ALMA. And in particular, we contributed to the detection of H2CS that we published in 2019 among a survey that we did of sulfur chemistry in 6 different protoplanetary disks. So H2CS was only observed in one of them, but in order also to interpret those observations and start to better constrain the sulfur chemistry in this astrophysical object, we developed a model, astrochemical disk model, to investigate what we are observing and interpret this. And in order to do this, so we based our knowledge on what we know already about sulfur chemistry in space. And what we know is the sulfur-bearing species that have been observed in other astrophysical objects, where they are much more abundant and there is a wider variety of sulfur-bearing species that were observed. So in this schematic, simplified view of chemical network, I resume the sulfur-bearing species we had at that time, noting that the blue ellipses are a dozen of species that were observed in L1544, which is a prestellar core in the past, and now in prestellar core there are probably twice more sulfur-bearing species, especially with all the recent work that has been done with the Yves telescope and with the team of Pepe Charnichao. But it's much more than what we have in this detected so far. We also have on this schematic network the sulfur-bearing species that have been observed in photodissociation regions. So they are highlighted by the species that are encircled with a black contour. And also we distinguish here the species that have been observed in protostellar envelope, so by Maria Dostovskaya in 2018, just to show a bit what are the beasts that are in each astrophysical environment. And so knowing that all these species have been detected, we can then build a chemical network in order to connect the chemistry of the species and try to find out what are the main pathways producing these species. So this network was used in our astrochemical disk model as a base. And what we need to precise here is that each arrow on this network is a chemical reaction that can be either in the ice, as represented here by the blue arrow. So the red arrow are for the gas phase reaction and the green one for the electronic recombination. So this is a variety of reactions. And for each of them, we need constraints from the chemist, both from the lab and from the theoretician, to constrain the rates and know what would be the major ones. So for this, we really need to work in close collaboration with chemists. But once we have constrained or tried to constrain the best that we can this kind of chemical network, then we can feed this into our astrochemical model. And so here, to remind a bit how this is working, so here is a schematic view of how work our astrochemical modeling. So where you have the code and all the box around show you what are the important input parameters to provide. So in red, you have basically the physical properties of this code. So on the left, we need first to have a good constraint on the structure of the source. So that is to say its physical structure, so the temperature, the density, the visual extension, the ionization rate, the UV flux, and also to know if we want to model how much dimension we want for our model. We also know we need also some constraint about the physical properties of the grains that are considering in our network, that is to say the temperature, but also the size and the shape of these grains. We need also constraint on the physical properties of the molecule, and in particular the binding energy of these molecules and how do they, at which temperature do they freeze, for instance, on grains. In purple here, I have represented the other key components, which are the chemical network that I just presented. That can be either pure gas phase chemistry or both gas grain or pure grains chemistry, depending on which layer, on which kind of object you want to model, and in particular in disk, which layer you want to focus on. We need also to know a bit, have some constraint on the chemical composition, that is to say the elemental and initial abundances that are considering in your network. And once you have all this input, you can run the model and compute the abundances of each chemical species that is included in your network as function of time. And usually we run this model up to a time that is the typical age, when we know it, of the source that you want to model. But so for the purpose of disk modeling, so we focus on the first box here concerning the structure of the source. And so I just previously showed you that disk looks to be pretty flat and pretty like donuts, but there are, so of course there is a third dimension, the vertical dimension, that is nicely represented here by this schematic view of Henning and Semyonov 2013, where you see that the disk is shaped by the central star mainly, and where you have here on the right different layers with a first layer that is photodominated, where you have mainly atoms and ions. Then in yellow you have a layer that is much more abundant in molecules, and especially the molecules are in the gas phase, and those are the ones that we can detect with ALMA and NOEMA, for instance. And then you have also a much colder layer, the ice layer, where most of the species are supposed to be frozen onto dust. And so for the purpose of modeling, so we only focus on this 2D vertical structure that we can represent much more in a much more simplified way as is. And we divided in two, so we consider that the disk is symmetric with respect to the midplane, mainly due to computational costs. And so we compute the physical structure for this disk. So that is to say the temperature profile, density, visual extension, and UV profile. So here represented at the bottom as function of 8 versus radius. And once we have this physical structure, we then compute the chemistry. So the chemistry is post-processed. And we can have, for instance, the abundance of CS, which is the most commonly sulfur-bearing species detected in disk. But in fact, we can have this for all the species that are in our network. And so here I'm depicting 9 of these sulfur-bearing species that are of interest for sulfur chemistry in disk, where 6 of them, as I was telling you, have been discovered in disk so far. But what is interesting when you look closer to this distribution, so this is a 2D density of each of the species, and you see that each of them is probing a different layer in the disk, and that even some of them are showing some structures, so such as gap and rings. So if you look at SO on the top right or SO2 on the middle left, you see some gaps. So that is also an interesting result from our model, because what you have to note is in that model, the dust is homogeneously distributed. So we can have structure without dust structure. We can have structure in the gas without dust structure. So this is an interesting result from our modeling computation. But for the remaining, I'm going to focus especially on CS and H2CS, because these are the species that we have been observing during the past year the most in protoplanetary disk. So as I was mentioning before, so we used ALMA to probe 6 protoplanetary disks that are listed here on the middle row. So in the middle row, you have the emission, the continuum emission map for each of these disks. And the bottom row is the CS emission in each of them, where you see, we can already see from this map that CS is much more extended, the CS emission is much more extended than the continuum one. So maybe it's more obvious when you look at the radial profile distribution of the continuum on the top row versus the CS emission on the bottom row. And interestingly also is that in some of these disks we see rings. So if you look at E46 ZAJ, which is the first disk on the left, you see a ring already that was already observed here from the moment map. But so there are also some structures that we observed in CS. And we were lucky enough to have, for two of these disks, several rotational transition observed for CS, which allows us to have some estimate to assess the column density and excitation temperature of these molecules in MWC 480 and Lead calcium 50. And so we compare those results with dedicated models that we built. And so here on the right, I'm depicting the column density as function of radius for the models, which are the continuous lines, and compared to the observation, which are the rectangle box. So you see that for CS, our model is not so bad in reproducing the column density of CS and also the excitation temperature of CS. So for this, we were already happy that we can model CS. We also got some CS isotopologues, but with very fainter detection than the main isotopologue. And in fact, the detection that is confirmed is only in one of these disks. But what is interesting already is that we have isotopic ratios that are much more lower than the one in the local ISM. So we still need to further observe isotopology of CS to check if this is due to optical thickness of CS or if there can be any fractionation occurring in this disk. So this is not clear yet, and we need further investigation to be checked, and especially to try to answer to the question if there is any chemical reset or chemical inheritance in disk from these ratios. But as I was also mentioning before, we detected H2CS. So H2CS is only detected in one disk, so MWC 480. And for this, from this detection, so we got 3 rotational transitions. So we were able to do the same exercise as we did before. So that is to say, to derive the column density and the excitation temperature of CS. And what we found is that the H2CS over CS ratio is 2/3, which is much higher than the H2S over CS ratio that was found in another disk. But still, this was really intriguing, and maybe it's telling us that there is maybe a sulfur reservoir that is more organic than we thought before. But when we compare our results to our models, we found that we couldn't, in fact, we underestimate the column density of CS by more than 2 orders of magnitude with our generic model. And so there is probably some chemical pathways that are missing in our model. So for this, we need to further investigate the chemistry with chemists. And I saw that maybe we have some hints from yesterday. So I would be happy to discuss with the people who've been working on the formation of H2CS and ICES, especially with new pathways. So for this, we would need to further constrain our model. But we were also able very recently to probe the chemistry at what we say planet forming scale, so at even better resolution, spatial resolution that we had before, thanks to the ALMA large program MAPS. So MAPS stands for molecules with ALMA at planet forming scales. So this large program was led by 5 co-PIs, and the main PI was Karin Oberg, where we decided to probe 5 disks, which already present some signs of ongoing planet formation. So we use for that 4 spectral settings across the band 3 and band 6 of ALMA to probe 20 species, including 1 sulfur-bearing species, which was the CS221 transition. And so we have already a bunch of results that you can find at the website that is indicated on the bottom left of my slide. So we'll already have 20 publications about these results. But here I'm going to focus on what we did about the sulfur, so the CS221 molecule, that was observed in the 5 disks, so detected in the 5 disks. So you see here again, so on the top are the continuum map. The middle row is the emission of CS221 that we extracted from each of the disks. And on the bottom, the radial profile. So in blue, the CS emission, and in gray, the continuum. So we can still see that the CS emission is much more extended than the continuum, but you also see some different shapes from one disk to another, where you have some peak intensity closer to the star, not in all of them. But maybe more intriguing from these maps, especially if you look at the moment zero maps, which are the middle row, is that for some of these disks, we have some asymmetries that were found. And so if we zoom on the IS209 disk, and we decided to look it to have a closer look at the disk and really extract the emission with respect to the major axis of the disk. So on each side of the disk, so the near side from us and the further one. And when we do that, we see that there is indeed a difference in the integrated intensity that we would be able to extract. And so we don't know yet what could produce that, but in order to be a bit more systematic, we did this investigation for the 5 disks that we observed in CS. And we were able to find that, in fact, this asymmetry is seen in 4 of them. So all the disks but IM loop, but maybe IM loop is a specific one because you see that the CS emission is super faint, so it's very hard to say anything in that disk. But we saw, interestingly, that it's not always the nearest side that is the brightest one. So for instance, in MWC480, you see that the further side is the brightest. So it's probably not due to artifacts from the observation, but maybe there is something occurring in this disk. And what we found is that in this 4 disk, there is signs for jets or outflows that are launched. And in particular in the HD 163296 disk, we know that there is a big outflow coming. I mean, there is some materials coming which is perpendicular to this asymmetry. So we don't know yet if there is a link in between this jets and or wind. We don't know exactly what are those. But if there is a link in between this and the fact that we see the asymmetry, we still don't know. Maybe it's uncorrelated and related to other effects that are occurring in this disk, but this we need further investigation to be constrained. But what we were also able to do from all this observation that we had previous to maps, and in addition with the 5 disks that we're observing maps, so we collected in total a survey of 11 disks in which we are able to derive the CS column density. And what we see is that maybe intriguingly that the CS column density is rather flat across this disk, and there is no specific trends depending on the size of the disk, the age, or the stellar type of this disk. So CS seems to be pretty constant. And we were also lucky because we serendipitously covered C2S and SO within the MAPS large program. And so unfortunately, none of them were strong detection. So we stayed conservative and only extracted upper limits. But upper limits are already enough to provide constraints on the column density ratio of some of these molecules. And so we used those first constraint to benchmark this result with our model. So we did that in particular for the CS over SO ratio. So we derive a lower limit that is represented here in gray in this plot. And with the model I presented previously, I ran a grid with several C over O ratios ranging from 0.5 to 1.5 in order to see first if we have any sensitivity of the CS over SO ratio with the elemental C over O ratio. So we see that only from the model, the CS over SO ratio seems to be a promising probe for the elemental carbon over oxygen ratio in disks. But for this specific disk in particular, we saw that we were able to constrain that in MWC 480, we need a C over O ratio that is at least 0.9 in order to reproduce the lower limit that we have. So this was already an interesting result and confirms some previous results that we did with other observations, nitrile observations, for which we built a specific model also and found that also we need a C over O ratio that is closer to 1 in order to reproduce the codon density that has been observed for CH3CN. So here we stay consistent. And in the collaboration, the MAPS collaboration, there have been other models used, so especially the Michigan model, where they were trying to interpret the C2H and CH observation that we had with the maps. And they also found that we need a C over O ratio of at least 1 and even above 1 to reproduce the observation. So we don't know yet what this C over O ratio greater than 1 is probing. And in this specific case of maps using the CS over SO ratio, we decided to extract this ratio in all of the disks that we had. So we see from the right plot that the CS over SO ratio is almost always greater than the one in MWC 480. So if we generalize our model, this probably means that the C over O ratio is of the order of 1 in most of the disks in order to reproduce the observation. So we still don't know what this is telling us, but maybe we have a hint that the C over O ratio is high in most of the disks. But we will need to do a further investigation on that, use other probe, and also to have a higher spatial resolution observation in order to probe if the C over O ratio can vary with the radius in the disk. So this will be interesting to pursue. But what we also did is to try to investigate the sulfur chemistry in other, to compare the results that we have in disk with the ones that are observed in other objects. So the one I just presented before, so prestellar cores, in particular the L1544, where a lot of sulfur-bearing species were observed. We also used the published data of the Orsted nebula, where species have been observed both in the photodissociation region of the Orsted, but also in the denser region that is assimilated to be a core. And when we do this comparison, we see that it looks like the sulfur chemistry that we detected is closer to prestellar core chemistry. So maybe we are probing the cold chemistry in the disk. But so for this, we will need also to have more sulfur-bearing species detected in disk to better constrain where the sulfur chemistry is occurring in disk and what is the layer that this is characterizing. And to finish, so we started to explore the sulfur chemistry in an earlier phase, so which is not the protoplanetary disk stage, but just before, so the class 1 stage, where the disk is already forming, but is still embedded in its protostellar envelope. So this observation has been performed with the IRAM 30-meter telescope, so we are not resolving either the disk or the envelope emission. But we decided, because we had a lot of sulfur-bearing species detected, to look for trends, and especially to look for trends of the ratios that are already identified to be chemical clocks or a good probe for the carbon over oxygen elemental ratio. So we didn't find any very strong trend, except maybe the CS over C2S ratio that is increasing with the disk to envelope mass ratio that we use as a proxy for the age of the sources, or the SO over SO2 ratio that is decreasing with this ratio and so the age. But for the moment, this is still an ongoing project for which we need higher resolution observations, and for which we will need to go with NOEMA or ALMA to better probe the physical component in each of the objects. So I think I'm going to probably stop here with a summary of my talk. So just to summarize that with the new facilities that we have access to, and especially the new sensitivity and high spatial resolution, now we can really study in detail the chemical composition and the structure of planetary disk. So in particular, we are able to map out the most readily observable species, that is CS. We still need to understand what the asymmetry that we are seeing in this disk, from where they are coming from, especially because they are not observed also in the other species that were probed in maps. An interesting other result that we had is that the H2CS over CS ratio is very high as compared to we expected and as compared to our models. So we need to understand why we find this result and what this is due to. So do we have, for instance, a more organic sulfur reservoir than we thought? This needs also more characterization. We need to look for other species in disks, but not only in the gas phase, but hopefully soon with the James Webb also in the ice, to better know where the sulfur reservoir is. And for this, we are lucky enough that there will be some data that are going to be taken in disks in the near future with James Webb, because there are already GTOs and GEO programs that are going to probe the 5 disks that were observed with the large ALMA MAPS program. So for this, stay tuned. And also we still need to improve our modeling, even if we already probably can say that the CS over SO ratio is a promising probe for the carbon over oxygen ratio. That it's very likely also that it's very common to have a C over O ratio that is almost or close to 1 in lots of disks. Even if recently we saw that in the disk where SO and SO2 are detected, it seems that it hints for more oxidized chemistry. So this is also something that we need to further investigate. And also we need to constrain the C over H ratio, so the total amount of sulfur that we have in disk, in order to better understand what is going to be inherited in the later stage, and likely in the comets that are going to form in the disk. So I'm going to stop here, and thank you for your attention and take your questions.
Questions? Well, I have some questions, Roman. I was curious because you saw that the sulfur elemental abundance in MWC 480 is about 10 to the minus 6, no?
Yes.
And this is quite a lot. This is the is this number really the sulfur elemental abundance in your model?
Yes, no, in fact, here I'm not showing all the grids I did. So in fact, I did a grid also for the sulfur, for the initial abundance of sulfur, varying from the much more depleted one up to the cosmic abundances. And here I'm only showing the value that is closer to the one that is observed in photodissociation region. And so because it was the one that was fitting the best, the observation was this sulfur initial value. But you're right that it's closer to what is observed in photodissociation region than a denser and colder environment. But we will need to have, you're right that we will need to have also this being investigated in other disks to probe the S over H ratio.
Yes, because in your conclusions, you say that you find a large variety in the number of the sulfur elemental abundance. Do you find any correlation with something, the spectral type or?
Yes, no, we don't. No, I did so for this one. Indeed, I tried to find with the spectral type the temperature when it was approximately constrained, or also the age of the source, and we didn't find any specific trend. But probably because we only observed CS for those disks, so it's not enough. I think we need to have more species observed if we want to find specific trends, or maybe ratios observed in all of these disks. For instance, the CS over H2CS, or even I think to have H2S observed in all of these disks would be great in order to provide some better constraints.
Well, any other question? Because I can go on a bit more. Okay, I can go on a bit more because I am the only one asking. Have you explored the possible influence of the prephase on the chemistry, on the disk chemistry? Because I suppose that in your model you have a prephase.
Yes, yes.
And exactly. Then you have the model. Have you explored that if you change the density of the temperature in the prephase, if it changes the chemical composition of the disk?
This we didn't. I mean, the only thing that we changed, we explore in the prephase are the elemental abundances. But you're right that we didn't. So the prephase is considered to be a molecular cloud evolving up to a couple of million years. So we explore the age of the prephase and saw that it wasn't impacting that much the results. But you're right that we didn't explore the physical parameter of the prephase, and that would be another interesting parameter to probe. To investigate. You're right.
Okay. Yeah. One question, 2 questions. Wait, they have to come here.
Okay.
Roman, thank you so much for the talk. It's Maria. I had a question actually about the plot that's up right now. So you're saying that CS is rather flat, but I think a few slides earlier you also said that you were suspecting that CS is optically thick. Are you worried a bit that you're seeing a flat curve because of the optical thickness?
Yes, no, that's a really good point, indeed. So yes, because we were afraid of this, and probably CS is optically thick in some disks, and I think the optical thickness can change also with the radius. That we investigated a bit in the previous paper. But really, I think to better constrain that would be great to have other CS isotopologue observed in each of the disks, because there is only one disk here, so it's lead calcium 15, for which we have strong, not strong detection, but confirmed detection of 13 TS and 634S, but this is the only one, and they were very faint and not radially resolved. So I think we need more observation of CS isotopolog at better sensitivity and higher spatial resolution in the disk to answer. But you're right. The optical thickness is probably linked to the fact that we are not seeing any specific trends.
Okay, gotcha, thanks. Maybe quick second question. Are you surprised that for the dust trap, the IRS-48, they have SO, SO2, 34, S2, but not CS? I don't know. What are your thoughts on this?
Yes, I quickly said on the conclusion slide that in some disk we have strong detection of oxygenated sulfur-bearing molecules, and I think it's probably linked with the carbon over oxygen ratio. That is to say that if indeed the carbon over oxygen ratio is very low, then you have more oxygen available in the gas phase to produce those the oxygenated sulfur-bearing species, and then you have less carbon to produce the carbonated one. So I think it could be related to the carbon over oxygen ratio, or in other words, to the reduced versus oxidized chemistry that can occur in the disk. So I hope I answered the question.
Okay, to talk here. Okay. So you say that the C over O ratio that you infer for the gas from the CS over SO ratio, it should be roughly 1 in the gas. Over which extension of the disk? Is this an average value, or it's resolved and you see that it is constant?
Yes, no, you're right. So this is mainly an average value, and so the next step is to be able to constrain the C over O ratio radially. But for this, we would need to have also, once again, a higher spatial resolution observation to really be able to do this work. Because if you look at, the value I was showing is just average. Over 280, 120, so the observed values that we have. So now the next step is really to be able to radially resolve this, and probably we're going maybe to see that it's evolving with the radius.
Okay.
Which will be, for which the people who are working in the exoplanet field are looking for, because if we can constrain this overall ratio as function of radius, they would be happy, I think. But we are not yet there, I think, with the data that we have, at least.
Yes, I was coming from the planetary formation perspective, actually, because in the models that we run, the chemical scenario we consider when we're doing the simulation for Ariel, we see a C over a ratio of the gas of 1, in reality only one of the scenarios. So if it is inheritance and with a low chemical activity, you get that. Otherwise, in the outer region, you see that the more chemically active the disk is, or the more you move toward the rosette, you see the CO going down below 1 markedly. So that would be quite interesting in getting an idea of which kind of disk chemical scenario is the dominant one that we should focus. Look forward to see the next results then.
Yes, thank you.
Okay. Thank you, Roman.
Thank you very much.
So I hope you can follow the rest by YouTube, and thank you very much for joining us today.
Yeah, thank you very much, Ascension.
Bye.
Thank you. Bye.
Hello. Yes? Do you have my presentation there? Hola. Yes. Hello. Okay. So, thank you very much for the invitation. Thank you, for Asunción, for organizing this small but very nice and focused workshop. So I'm going to talk about sulfur chemistry in UV-illuminated molecular clouds. So this happens, of course, in the diffuse ISM, low-density ISM clouds, but also everywhere in star-forming regions, everywhere you have molecular clouds close to massive stars, and we have a lot of UV radiation. So I would also like to say that we work here in the Instituto de Física Fundamental, which is like 1 kilometer following the street. So I'm working with Pepe Cernicharo, Octavio, which is in the room, Raúl, with I think it was in the room, and Marcelino Agúndez, so not far from here. So this is the brief outline of my talk. I will try just to this community to stress why sulfur is so relevant, but also why it's so peculiar in astrochemistry. I will tell you again what is a PDR and what are the main aspects of the photochemistry taking place in PDRs. And I will present you the starting points, the first reactions of sulfur. So how sulfur starts, which is how do we go from sulfur plus or sulfur atoms to the first sulfur hydrides. Okay, then I will try to discuss briefly some aspects of the gas phase and the grain surface chemistry of these hydrides. So you know that sulfur is in the top 10 list of the most abundant element of the universe. We know also this. So this is a plot of the abundance of different elements in the diffuse ISM, so very low density clouds, okay? And these elements are plots as a function of the condensation temperature. So you have here that 0 means that the abundance of the element is the same as in the sun, okay? So no depletion. So you see that the more refractory elements, like iron, you know, and these heavy metals, even in the diffuse gas, they have very low abundance compared to the sun. This is because even in the diffuse gas, all these refractory elements go into the grains, okay? They form silicates and so on. But we have also in the other extremes, these volatile elements like carbon. They are very volatile, but they are a bit depleted even in the diffuse gas. This is because you have also in the ISM carbonaceous grains, okay? So in between, you have sulfur, which is less volatile than carbon, but you see that it's not depleted. That is to say that most of the sulfur is in the gas phase, okay? So we see the same abundances as in the sun. This is a bit contradictory because in interplanetary dust particles, we see sulfur in this rocky material, and also in the atmospheres of evolved stars, we see solids that contain sulfur. So of course, we are all interested here in what is the level of sulfur depletion in different environments and where is sulfur in all these kind of environments. So in astrochemistry it's important because sulfur is a low ionization potential element. It means that the UV photons can ionize it. So sulfur is a good source of electrons in many environments, and you know electrons are very important. As I have told you before, most of the sulfur in very diffuse clouds is in sulfur plus. Okay, this is the main reservoir. In molecular clouds, we are close to have like 40 molecules containing sulfur, but only one, sulfur 2H, contains 2 sulfur atoms. This was detected in PDRs by Asunción and our team. The problem, of course, is that if you add all the abundances of these 40 molecules in these molecular clouds, it only makes a tiny, tiny fraction of the total sulfur that we know exists in the universe. So the very old question is, where is this sulfur? Is it in ices? Is it in the rocky grains? Or is it in, for example, in atomic form? Of course, in the ices, we only have the clear infrared signature, the spectral signature of having detected OCS, okay, in molecular clouds, and solid H2S also in comets. Oops. So in the 80s, before people were talking about the freeze out of molecules and grain surface chemistry, people thought that everywhere you see a sulfur molecule, it means that you are observing a shock or a high energetic phenomena. This is because the gas phase chemistry of sulfur is very peculiar, because all the hydrogen abstraction reactions, so the reaction of S plus H2 to give SH plus, reacting with H2, etc., and also the hydrogen abstraction coming from atomic sulfur, SH, H2S, all these reactions are very endothermic, okay? These reactions have endothermicities much higher than the temperature that we have in the gas. So people thought that if you see, for example, H2S, it means that you are in a shock because you need temperature to overcome all these very endothermic reactions. So my laboratory is the PDRs, which means photodissociation regions. These are regions or molecular clouds where the chemistry and the heating of the gas is regulated by the presence of far UV photons. By far UV, we mean photons that cannot ionize hydrogen, so less than 13.6 electron volts. And this interaction of UV photons and interstellar matter happens at different fluxes of the far UV flux. So for example, in the ISM we have, and that we denote by G naught, so we have from G naught equal 1. This is the mean UV radiation field in the ISM. And these kind of low illumination regions are a good laboratory of normal galaxies, for example. But we also have regions like the Orion bar, where the molecular cloud is very, very close to a very massive star, so it's extremely irradiated, and here we can have UV radiation fields much higher, okay? And these environments are similar, probably, to what Roman has been discussing, to the inner layers of protoplanetary disks that are very close to the star, and they also have hot PDR layers. So PDRs are important in the ISM because this is the regions where we go from ionized to atoms to molecules, okay? The blue will be a molecular cloud, so the UV radiation field will be decreasing in this direction. So most of the star formation takes place here, deep inside molecular clouds, where the temperatures are so low that molecules freeze and develop ice mantles that cover the grains. But you have to realize that most of the ISM in volume, is in this domain, where the chemistry is really affected by the presence of far UV photons. Sulfur, because of its lower ionization potential, the transition from sulfur plus to atomic sulfur will be something like here, a bit deeper inside compared to the transition from carbon to CO. So my main two sources of study are in the Orion, in the Great Orion Molecular Cloud. One is the famous Orion bar, which is a PDR that is close to the trapezium star. So this is a very irradiated PDR with a UV flux like is 10,000 times higher than the average UV flux in the galaxy. So this means that the gas is warm, and also means that the dust temperature is relatively warm, so less than 50 Kelvin. And also the famous Horsehead Nebula, which is irradiated by a star that is here, but more far away, like 3 parsecs. So the radiation field here at the head of the Horsehead is something like 100 times the mean UV interstellar radiation field, which means that the gas is warm, but not so hot as in the Orion bar, and the dust grains are cooler. Okay, so this is the two main PDRs we are working on. So a long time ago, people thought that a strongly UV radiated PDR like the Orion bar was going to be very poor in terms of chemistry, because most of the molecules, even if they form quickly, they will be like photodissociated. So the chemistry in PDR is a bit different compared to the chemistry in dark clouds, basically because we have a lot of ions, C+, sulfur+, and we also have a lot of hydrogen atoms. This comes from the photodissociation of H2 molecules. Another difference is that we have a lot of electrons, so the ionization fraction is high. And as you will see in the next few slides, we also have a lot of vibrationally excited H2. Okay? This is H2 molecules that are pumped by the UV radiation field, and they stay in very highly excited vibrational states. So in fact, we did a survey with Sara Cuadrado in her PhD of the Orion bar with a 30-meter telescope, so in the millimeter domain. And in fact, this region is not so poor, so we detect a lot of lines, like more than 500 lines, 65 molecules. And these are the sulfur-bearing molecules that we have detected in order of abundance. Okay, so the most abundance will be H2S, and then we go SO, CS, SO2, all the way to HCS. Plus, here is a plus. And we also detect this very peculiar reactive ion SH+. Okay, so the chemistry is not so poor. So sometimes in the ISM, it's only a question of integrating deeper, and the same molecules that you detect in dark clouds, normally they appear in many other environments. Of course, the formation and the destruction is different in different environments. So compared to carbon, you see that sulfur has a lower ionization potential. So this means that the transition from sulfur plus to sulfur, it's a little bit deeper inside molecular clouds. So this is a model that we run with the Meudon PDR code, including gas phase chemistry in a very simple grain surface network. So you see that in diffuse clouds, most of the sulfur is S+. Well, by the way, the astronomers, we plot the depth into a molecular clouds, and we talk about magnitudes in the visible, so extinction in the visible. So this will be the edge of a molecular cloud that is irradiated in this direction. So this is very irradiated, and this is more shielded. Okay. So here in these regions, most of the sulfur is in S+. And you see here, for example, in this region, most of the electrons comes from the ionization of sulfur. That's why these curves are the same. Okay. So deeper inside, the photons will not be able to ionize sulfur, so we start to have sulfur and other sulfur-bearing molecules. And deeper inside, as those temperatures drop, you will start to grow ices in the grains. Okay. Of course, the ideal will be to observe the main reservoir, so to observe sulfur plus. So how can we observe sulfur plus or even sulfur? So this is a very peculiar element because compared to carbon, for example, sulfur plus doesn't have low energy fine structure levels. Okay, so we cannot detect sulfur plus in the far infrared. However, we can detect in the radio the recombination of these S+ ions with electrons. You know, these electrons recombine in very excited electronic states. You know, like it's like a big Rydberg atom. So these electrons recombine in very high electronic states and start to cascade, you know, emitting photons that we see in the radio. So this is a very useful way, in fact, of detecting sulfur plus and carbon plus in the radio. And well, I will tell you later. So these lines, these radio recombination lines of sulfur plus and carbon plus, they come from the PDRs, from these layers, okay? They don't come from the H2 region, from the ionized gas. So to detect this line, we use this very nice telescope, which is now, it has very modern radio receivers, and these are very good because they are very sensitive and they are very broad bandwidth, which means that we can cover almost 20 gigahertz in one shot. Okay, this is a telescope that is 100 kilometers from Madrid, in Guadalajara, it's a province close to here, and we can observe a frequency that we've been not observing, for example, with the 30-meter telescope. So with this telescope, with a relatively good angular resolution, we point to the Orion bar, you know, this will be the angular resolution, and you detect these lines that you don't see here much. Maybe it's better to stack the spectrum, you know. What we see is a very broad line here. This is a helium recombination line. So helium has an ionization potential of 24 electron volts, which means that helium plus comes from the H2 region, the ionized gas. But you see here two narrow lines, here in red and in blue. So this is a carbon recombination line, and this will be sulfur. Okay, so this is sulfur plus coming from the edge of a molecular cloud. So if you assume that both C plus and carbon plus recombine with electrons with more or less the same mechanisms, you can use the line intensity ratio, the carbon plus divided by sulfur plus intensity ratio, to constrain the carbon to sulfur abundance in this medium. So this is what we do. In Orion, we have observations in another domain taken with the Hubble telescope, and we know with high accuracy what is the elemental carbon abundance. It's something like 1.4 10 to the minus 4. Okay, so if the ratio of this carbon plus to sulfur plus lines is 10, this means that we can infer or in an approximate way constrain the abundance of sulfur plus at the edge of the PDR, and it's something like 1.4 10 to the minus 5. Okay, so this means that in the molecular, at the edge of the molecular cloud, and this value of course is the same as the solar abundance. Okay, so this means that at the edge of the molecular cloud, the sulfur abundance is the cosmic sulfur abundance. So all the sulfur is in the gas. Okay, there is not sulfur in grains or in somewhere else. All the sulfur at the starting of the molecular cloud is cosmic. Okay, so this is the starting sulfur abundance in the molecular cloud. Of course, the angular resolution of JBS is like 40 arcseconds. So if you want to see things in detail nowadays, you have to go to ALMA, and this is like putting the molecular cloud into a microscope. So this is very high angular resolution observations of the edge of a molecular cloud. So here the stars are here, the UV illumination is coming in this direction, and you see like molecules like CO, you see emission almost everywhere in the observed field. Okay, this purple map is an infrared map. This is the emission from vibrationally excited H2, and you see that you only see vibrationally excited H2 really at the edge of the molecular cloud, which are absorbing these UV photons here. And you see like molecules like SH+, okay, they only are bright also at the edge of the illuminated molecular cloud. Okay, and this is peculiar. SH+ is peculiar because this reaction S+ plus H2 is very endothermic, 10,000 Kelvin. So in principle, in molecular clouds, you will not expect to see these molecules. Also with Sophia this time, because this molecule, SH, the neutral radical, has very complicated frequencies that you can only observe from the stratosphere. We tried to detect SH with Sophia, but unfortunately we couldn't integrate as much as we wanted. So even if my eyes want to see here the detection, you know, this is below the 3 sigma, you know. But at least if you model this correctly, you have a very accurate upper limit to the abundance of SH, okay? And again, there's a reaction, atomic sulfur, the neutral atom with H2 is very endothermic, 10,000 Kelvin, so in principle you should not detect these molecules. So what happens? The thing is that in many UV radiated environments, the reactivity of the H2 molecule is different when it's excited vibrationally, you know, it's in vibrationally excited levels. And this reactivity is very selective, depends on the atom, you know, with who H2 reacts. So, for example, if you take this reaction, O plus, oxygen plus H2, this reaction is very endothermic, you know, so the formation of OH plus will be very easy, you know, and you will form a lot of H2. For the neutral oxygen plus H2, this reaction is endothermic and has a little barrier, okay? So it's more complicated. So if you go to sulfur plus, this reaction is very endothermic, okay? And if you go to the neutral atom, S plus H2, this is endothermic and it has a barrier, okay? So the key thing here is that when H2 molecules are in these vibrationally excited states, we can use the energy of these levels to overcome the endothermicity. So these reactions can become fast if you have enough H2 that is vibrationally excited. So of course, if you want to know the state-dependent reaction rates of these reactions, you have to collaborate with the people that know how to do this, and that's why we collaborate with Octavio Roncero and his team. And these are the reaction rate coefficients as a function of gas temperature, for example, for this reaction, S plus H2. If all the H2 molecules are in the ground state, you see that these reaction rates are very small and they will only be large enough at high temperatures. But if you manage to have H2 in high vibrational states, this reaction rate will be very fast, it's high, okay? For sulfur plus H2, this is a bit more complicated because it's endothermic and with a barrier, which means that this reaction, the reaction rate, they will always depend on temperature, you know, and in order to be a fast process, you have to have H2 in very high vibration excited H2 levels. And so the difference between these two curves is the presence of a barrier in the reaction of hydrogen with a neutral atom. So H2 is observed in very high vibrationally excited states. These are observations of the Orion bar, where people detect H2 up to V equal 12. Okay, so very high in very highly excited molecules. And this is a model, so again, the radiation is going in this direction. At the edge of a molecular cloud, you don't have much H2. The H2 molecule, the abundance is growing up. But you see here in this plot below, this is the abundance of H2 in different vibrational levels, that even if you have little H2 here, in this edge of a molecular cloud, most of the H2 will be in highly excited states, okay? And then if you go to deep inside a molecular cloud here, this will be dark cloud conditions, you have a lot of H2, but most of the H2 is in V equals 0, okay? And of course, the presence of vibrationally excited H2 affects the chemistry a lot. So we try to understand the first step of the sulfur chemistry in PDR, so we try to study this reaction, these hydrogen abstraction reactions with Octavio and his team, so to determine the state-specific reaction rates and see if this presence of vibrationally excited H2 could explain the presence of SH plus, SH and H2S in the Orion bar. So you don't see anything, but well, this is a table with the reaction rates. We try to be as precise as possible, so including all this state-dependent chemistry. Also for the chemistry, we don't use the standard photodissociation rates, but we do integrate the photodissociation and the photoionization cross-section. This is, for example, for H2S. Okay, so we integrate these cross-sections at every position of the cloud, at every radiation field in the molecular cloud. So this is the resulting model of the Orion bar. Well, here in this thin pink line is the SH plus abundance when you use the standard reaction rates. And here in the thick pink line is where you use the state-dependent chemistry. And you see that the abundance of SH plus is much more enhanced when you use this state-dependent chemistry. For SH the reaction enhancement is not very high, because you see that sulfur, atomic sulfur, where in the regions that you have atomic sulfur, you don't have much vibration excited H2. And for H2S, the enhancement is not high. Even in fact, it's lower because there are backward reactions with atomic hydrogen. So the thing is that we observe H2S in the Orion bar, so at the edge of the Orion bar. These are detections of H2S in the Orion bar, and we were extremely surprised because these ground state lines make like 6 Kelvin, so these are extremely bright, okay, at the edge of the molecular cloud. The model was, the pure gas phase model was predicting like column densities up to 10 to the 12, but from the observations we were detecting more than 10 to the 14. Okay, so there is a lot of H2S at the edge of the Orion molecular cloud, and well, by the way, the ortho to para ratio of H2S was close to 3. There is so much sulfur that we not only detect the 34S isotope, but we also detect the 33 isotope, so H233S, okay, and 33 sulfur is the only of the isotopes with a nuclear spin, which means that this molecule has a hyperfine structure, and you see all these tiny lines. This is the ground state line of H233 sulfur, okay? So there is a lot of sulfur in this region. However, we don't detect, for example, this interesting ion, H3S+, okay, we don't detect it, and this will be really the gas precursor of H2S. So if H2S was produced in the gas phase, we would have detected this one, you know, because a recombination with electrons will provide the formation of H2S. So one thing that we haven't discussed much here in this workshop is how do we go from line intensities to column densities of or molecular abundances. For this, we need excitation and radiative transfer models. And in the last years, thanks to a small funded program between CSIC and CNRS, people determine the inelastic collisional rate coefficients for many of these systems. So the most important one, the collisions of H2S with H2, that up to this year they were not existing, you know. So this information, the inelastic collisional rate coefficients, is in fact the ingredient that we need to convert the line intensities into accurate column densities. So the important thing in the Orion bar PDR is that if you compare the SH to H2S abundance ratio, you know, this ratio is much smaller than in diffuse clouds. You know, in diffuse clouds, SH is much more, well, it's more abundant than H2S, okay? So for some reasons, as soon as you are in a dense molecular cloud, there must be a very efficient formation route for H2S, okay? There is too much H2S compared to the gas phase predictions. So of course, what happens, probably the answer is in the grain surface chemistry. You can have the two approaches. You can think that before the stars start to shine and irradiate the molecular cloud, in the dark phase of Orion, molecules were accreting into grains and forming and developing ices. So, and as soon as we have UV radiation, these ices will start to photo-desorb or whatever. And you can also think that PDRs, maybe as the temperature of the grains drop, they start also to develop grain surface chemistry. So in addition to our gas phase chemical network, we also added a small, simple network of sulfur chemistry in the grains, where basically we only hydrogenate sulfur atoms, okay? So if these sulfur atoms stay long enough in the grain, meaning that they don't evaporate or they don't photo-desorb, they will start to hydrogenate and go all the way to H2S, and then this molecule can photo-desorb, okay? Although we also included a very easy prescription of the chemical desorption of this molecule. So basically in a PDR, because we have so much UV photons, it seems that the photo-desorption of these ices can be more efficient than the chemical desorption. So for this, in our models, we need desperately accurate numbers for the binding energies, and as I told you yesterday, for the sulfur chemistry, there is some discrepancy. So there are, the old models use these low binding energies, whereas in this recent calculation, these are calculations, they find slightly higher, well, slightly no, it's higher binding energies. And this, at least in the PDR models, has a dramatic effect, you know, because this determines the temperature where molecules start to freeze or evaporate. So if the binding energies are high, this means that molecules go earlier into the grains, okay? And they develop grain chemistry much earlier. So this is the result of grain plus gas models compared in continuous curves compared to a pure gas phase model. So the green curve is H2S. So in dash is when you only have gas phase chemistry, and you see the dramatic increase of H2S when you allow to develop H2S ice mantles in the grains, and you allow for photoabsorptions of these ices. So in these models, of course, the column densities of H2 that we predict in the gas phase are much closer to those that we predict in the pure gas phase models. So how much time do I have? About 5 more, or how much? Okay, so I have time. Okay, so that was the Orion bar, which is an extremely radiated PDR. So now we go to another PDR environment, which is also interesting and perhaps more representative of the average gas in normal galaxies, which is the Horsehead. Now the UV illumination is lower, okay? So grains will be always cooler. So if the grains are cold, this means that these grain mantles, they will not be able to sublimate, okay? So the only way to put these ice mantles off the grain will be either non-thermal desorption, like photodesorption, or chemical desorption. So these are observations of the Horsehead with the 30-meter telescope, okay, where we detect almost the same molecules that we detect in the Orion bar, okay? So here you have the abundance of, for example, H2S. So all this, if you add up this, the abundance of these molecules, of course, you get a very small number compared to the cosmic abundance of sulfur. See, here you have the Orion hot core, which is a different environment, and you see that the abundance of H2S is much higher. It's something like 10 to the minus 6. So this is a hot core. It means that you have the grains the ices covering the grains, and suddenly the protostar starts to heat up the grains, you know. And in these hot core environments, the abundance of H2S can be much higher. So for me, this 10 to the minus 6 is will be like the maximum abundance of H2S that you can have in the ices, you know, before sublimation. So of course, in this observation, we also don't detect many sulfur-containing species. So these are the species that Asunción and Pablo and we looked in the spectra. So this, of course, means that these are not the major reservoirs of sulfur. But then we come to this very peculiar detection. This is the first molecule containing 2 atoms of sulfur. And so far, we have only detected this molecule in this particular environment, a low illumination and cold PDR. It's the first doubly sulfurated molecule in the ISM. It's not present in the Orion bar. It's not present in hot cores. It's not present in comets. So why is it forming in an environment like this one? Well, in fact, it was searched in the 67P comet, and it's not there. You know? But in the Horsehead, this ratio, S2H over H2S, is very high. Well, basically because we detect S2H. So as Guillermo told you the first day, people were very excited with this detection, because when you go to the lab and you grow H2 ice mantles and you irradiate it with UV photons, you start to create molecules containing sulfur-sulfur bonds. So we thought, okay, yes, this is probably the trace of the photoprocessing of sulfur grains in the ISM. This was the experiment they did in the high ultra vacuum chamber at CAP, you know. So when you irradiate with photons and pure H2S ice, you do see the photodesorption of this molecule. He talked about this on Monday. However, you don't see the photodesorption, sorry, of molecules containing sulfur 2H, okay? So why we only detect S2H in the Horsehead? So probably, at least what we think now is that probably H2S, you can form it in grain surface. So this will enhance the abundance of H2S in the gas phase, okay? But then we also have a gas phase photochemistry triggered by the presence of sulfur plus everywhere you have UV photons. So probably the reaction of sulfur plus H2S forms this ion, S2H2 plus, okay? You can also form this ion through reaction of SH plus H2S, okay? And if you have this ion, the recombination can lead to S2H in the gas phase, okay? Unfortunately, and this is a work for theoreticians, we don't have data on this particular reaction, but so far is the only way we think we can form H2H. Because it's very weird to detect H2H in the Horsehead and not in the Orion bar. Another possibility, and maybe I will favor more this one, is that this molecule is very reactive. So if you have oxygen or nitrogen, it will react with oxygen and nitrogen. So perhaps in the Horsehead, because it's much cooler, the oxygen atoms have started to freeze out, compared to the Orion bar, where we still have oxygen atoms in the gas. And maybe that's why, maybe the reason is that in the Horsehead, the destruction rate is much lower than in other environments. But this is a very peculiar molecule. It opens the detection of other molecules containing two sulfur atoms, but it's been now 5 years, and this is the only place where we have detected this molecule. So to conclude, we have detected sulfur recombination lines in Orion molecular cloud, and this means that at the surface of Orion, the elemental sulfur abundance is just the same as the solar abundance, so there is no depletion at all of the sulfur elemental abundance, at least in the surface. So this means that we cannot have much sulfur in the grains as rocky compounds. We have detected SH+, again at the edge of the PDR, and this can only be explained by reaction of sulfur+, which is very abundant, with the presence of UV pumped H2. And again, when you do the models, this to reproduce SH+, we cannot, we don't find that we need sulfur depletion from the gas phase up till AV equal 2, which means that you don't, of course, and this is, well, we all know this, you don't start to form ice mantle until you go deeper inside the molecular cloud. And we have detected very bright emission from H2S in the 3 isotopes. This is very peculiar because up to now, the detection of this isotope was only toward very rich and bright hot cores. So pure gas phase chemistry cannot explain why we have so much H2S in this kind of UV-radiated environments, and we have to think that this is this can happen only because somehow you are forming H2S in the grains, and very easily this H2S has to go back to the gas phase. And with this I conclude, and I thank my team, my collaborators, and my, how do you say now, sponsors? Funding. Thank you.
Thank you very much for this brilliant talk. And my question is related to the H2S detection in the Orion bar. And I would predict, if it's chemical desorption, that you would have an anti-correlation of the presence of H2S and the water formation. Because when you do have water on the surface, it reduces a lot the chemical desorption. So to say it, on bare grains, you would have almost 100% of return in the gas phase as H2S, but when you add up some water, it absorbs most of the energy, and then it's less and less efficient. So I would, usually we said that the water layer appears at about 0.3, 2 or 3 AV. Could you comment on that? Do you know where?
I mean, the models, I must confess, they are not they're not extremely accurate. It's like a toy model. So
yeah. Anyway.
Anyways, in a PDR like this, with the amount of UV photons that we have, the models say that the photo desorption will be more efficient. Deep inside the molecular cloud, you lose the UV photons, and this is the only place where you can have the chemical desorption. But the efficiency depends a lot of the matrix, no?
Yes, so my question is, do you see a special evolution of H2S, or is it not resolved? And then is the cutoff or the reduction of H2S in this case coherent with the presence of molecular mantle on your grains? Because if not, if you are in the photodominated region, then you have a bare grain. That's the best way where to observe the chemical desorption. Just an example, if you do form the water on graphite, you have 80% of loss, and if you form the water on water, you have 10% of loss. So having this is
The thing is that we only have very precise observations toward the edge of the Orion bar. We don't have the same kind of detections deeper inside. Okay, only the ground state line of H2S is true that remains like constant. You know, so it seems like H2S does not disappear.
Okay.
There have been other kind of observations in dark clouds where you see really that H2S does not disappear.
Yeah, yes, but you detect a lot of H2S.
Yeah, but I only have like spectroscopic information of the very edge, you know, so it's more complicated to me.
Well, it's a question of a comment. Because I agree with you that we have to go back to the horsehead, because I remember that you some years ago derived a sulfur elemental abundance with a depletion of a factor of 10 in the horsehead.
4.
Well, and this is a bit different than in Orion, that you have no depletion at all. So probably there are some other differences.
Well, I think in the horsehead, that was what, 20 years ago, and
yeah.
Relying on chemical models. But in the horsehead, I think you are really, in your observations, you are dominated by AV equal 5 or something like this, where in the Orion bar, in the observations, you are really dominated by low AVs.
Yes, but well,
yeah, but the important thing.
But in principle, we are looking at the elemental abundance, not on the gas phase. So even if you have ice in the horsehead, well, it seems that there is a difference with Orion.
Yeah, but remember these 20 years ago models, they were pure gas phase models, you know.
But they are very good. They were very good, Javier.
No, I get it. A factor 4 in astronomy is nothing, you know. I mean, if you tell me that the horsehead is a factor 100, you know, I think the message is that sulfur is very abundant, much more abundant than we at this in diffuse gas for sure, and at the beginning of the molecular growth history.
Okay.
Sorry. Gisela.
Just a very simple question. Have you tried to look for S28 in another type of PDRs? I mean, with the same condition?
No, I only work in horsehead. I am very loyal. I only work in horsehead and Orion bar. But for example, she works in NGC 7023.
In other PDRs with similar conditions and.
Okay. Well, we need to do it deeply, but I searched for S2H in the spectral survey of Paolo Pileri in NGC 7023, and we didn't find. Of course, we can go to more sensitive observations.
The good thing of the Orion bar is that it's so bright that we detect many lines of H2S, so we can do an ortho and para H2S, so we can do a very fine job constraining abundance column densities in the horsehead, because it's fainter, you only see one line, you know, and it's more complicated to constrain the column density, I think.
An assessment that, in fact, you mentioned that the sulfur was in the gas phase at the very beginning and so on, but strictly it's not completely true, you know, because we know for many years presolar grains, and in presolar grains silicon carbide you have also contents of sulfur. It's really minor, no? And probably presolar grains only participated in a really small amount to the materials accreting.
I put it in the first. In the first slide, I say, but still there is a margin in the depletion, but it's really small. So
very small.
And this is still surprising, I think. So now that you say in the AGP community, they detect solid grains containing sulfur, but some of them they say that can be only like at the surface of the core of the grain, that these rocky sulfur compounds can be fragile enough so that when you go to the ISM, they are destroyed.
Okay, we'll move to the next presentation.
Okay, apologies for the technical. 2 computers later, we're there. Okay, one more moment. I can go? Okay, all right. So thank you, everybody. Honorary last talk of the day. My name is Retransmisión. It's my pleasure to be at this Sulfur workshop and to tell you about the sulfuric links between star-forming regions and comets. So this will go a bit in the direction which Asunción was presenting at the very beginning, where we try to link the different stages from the earliest to the latest, i.e. comets in our solar system. So as we're all here because we are big sulfur fans, I will skip the whole introduction on sulfur depletion. I think we've heard it several times now. Sulfur is very interesting. It's found in amino acids. They're essential for us. On the other hand, we should definitely not be in contact with it for too long. It can be quite dangerous. So a very badass element that we all love. So for me personally, the interesting research question is that of linking the different stages of star formation with some of the remnant relics of earliest stages of formation of our own solar system. So the whole link from prestellar cores, I think, will be covered tomorrow morning by a few talks. Protoplanetary disks in between, as summarized by Roman, and then comets, which are also already introduced by Dominique. So what I want to know is, are there any chemical links between all these different stages? And if so, in what molecules are they there? In what isotopic ratios and so forth? Now, of course, it's possible that everything's preserved, it's possible that everything is reset, or it's possible that there's some sort of partial preservation between these different stages. And now this is going to depend on the degree of thermal processing as well as the degree of radiative processing, thanks to the chemical processes that take place in the ISMs. So some of the things we heard about yesterday. It's going to depend on the timing and the location of our cometesimals. And as hinted at by Diego earlier today, also depends on dynamical evolution of the cometesimal. So once it's formed, where is it going to go? In my talk, I'm going to focus on the hot inner regions around low-mass protostars, the so-called hot carinos, and the molecules that we find therein. And the argument I will use as motivation for that is that in cores and in protoplanetary disks, in particular in protoplanetary disks midplanes, the temperatures are low, so you're going to freeze out many of the volatiles. So perhaps it's a good idea to look at the warm inner region, where we expect all the volatile inventory to be thermally desorbed, so we can peek into the full inventory easily. So in my talk, I will look at these hot carino regions in terms of their chemistry, and then I'm going to look at comets as well. Oh no. Okay, so I will look at the hot carino regions in terms of their chemistry, and then I will link it with comets. Now, the reason of linking it with comets is because, as Dominique already told us today, comets are thought to be pristine relics of earlier stages of formation of our solar system. Comets are some of the most distant residents of our solar system, so they're very far from the sun and the thermal heating that it causes. In terms of their kilometer-sized nuclei, they are kind of intuitively some sort of stepping stone or a byproduct of forming full-fledged, much bigger planets. It's thought that comets, and in particular the molecules that are within their nuclei, they trace the innate protoplanetary disk of our solar system. And I think there's quite some good evidence for that now. So for example, it's been shown that cometary nuclei contain some highly volatile species and also in appreciable abundances. So over here I'm quoting some numbers that came from the Rosetta mission for Comet 67P, where we have CO, N2, molecular oxygen, and even some noble gases trapped at as high as, for example, 3% relative to water in 67P. So this presence and the high abundance of these highly volatile molecules is suggesting that cometary nuclei suffered little thermal processing. And thanks to many decades of ground-based observations, and of course also the Rosetta mission and other preceding missions to comets, we know that they carry a diverse set of both simple and complex molecules. So now I will jump into the chemistry of a hot corino. For my case study here, I have the hot corino around the low mass IRAS 16293-2422, and I will focus a lot on this hot corino as well as Comet 67P, not particularly because they're my favorite, but because they have some very exceptional data sets. So it's a bit more of a data-driven motivation in this case. So IRAS 16293 was studied with ALMA, the Atacama Large Millimeter Array, on small spatial scale, so this is a big perk of ALMA. It is in principle, as we now know, a triple source. In the schematic you have source A and B, but in fact source A splits into A1 and A2 further on. With ALMA we carried out the so-called unbiased protostellar interferometric line survey, abbreviated as PILS. And this was a wide frequency coverage that was surveyed towards the source with ALMA at a high sensitivity as well. So here are small examples of what you can see towards the source. So actually top panel here is the full frequency range of the PILS survey. So this was ALMA band 7, so roughly 330 to 365 gigahertz. You see a massive forest of lines, and if you zoom in into smaller and smaller sections, then you can actually come to appreciate that it's not just noise, but in fact it's all individual lines. Now, I will spend a lot of time analyzing source B, simply because towards source B we have a preferential geometric orientation. The disk around source B is face on, and the lines are much narrower. So you can actually disentangle all of these individual peaks. If you look at the same section of the spectrum towards source A, you have much wider lines, and then you're going to suffer from line blending, and it becomes a lot harder to pin down accurate column densities and excitation temperatures, and to uniquely identify your lines, really. So essentially, we're very lucky with IRAS 16293B. To summarize what came out of just under 34 gigahertz of data with ALMA, there were roughly 10,000 lines in the spectrum. And in the end, now that we've spent a few years analyzing this data, and quite a few papers have come out on this, 100+ molecules have been identified towards this source. The column densities that these molecules span, if you draw this line of where your methanol column density should be, they span 5 orders of magnitude. So all in all, this is telling us we have a huge chemical diversity and complexity towards the source. And in the yellow box, I've highlighted the sulfur-bearing species towards this source. And just by quick by-eye inspection, you can see that several of them are actually quite abundant. So sulfur-bearing species are definitely not a minor player in the chemical inventory of IRAS 16293B. So I've stressed the frequency coverage of PILS, and I'll just add that the wide spectral coverage that we obtained with the survey was very important to secure many of these identification, because a wide frequency coverage allows you to carry out multi-line observations rather than just 1 or 2. So this allows you to have secure detections by multiple lines. It automatically helps you determine much more accurately your column density and your excitation temperature for your molecules. And another key feature of the survey was its sensitivity. Many molecules, especially the most abundant ones in star-forming regions, once you start looking at the hot corinos, are going to suffer from opacity effects. So their lines are going to be optically thick. With pills, we were able to get the minor isotopologues of many of these. So then if you assume a local ISM, isotopic ratio, you can get a much better handle on the column density of your main isotopologue. So for example, to get methanol in this source, we use the 18O isotopologue to get its column density, because methanol itself and even the 13 carbon variant are actually optically thick. So as it's a sulfur workshop, let me focus in a bit more on the sulfur-bearing species. So as I mentioned, some of them are quite abundant. We got simple carriers, your classical SO, SO2, OCS, H2S, CS, diformaldehyde. We also have isotopologues of these. You have the sulfur isotopologues, so 34, 33, oxygen, 18O, 17O, carbon, silicon, and also, of course, the deuterated variants. So OC33S was a first-time detection towards the source. Tentatively, with one line, I think we also have C36S, actually. I like that one quite a lot. We also found some complex species, CH3SH, but unfortunately, no isotopologue detections, not even CH3SD. So perhaps for that, you may have to go even deeper. So just the takeaway from this is that the inventory of sulfur-bearing molecules in the hot corona of source B is diverse, and the most abundant of these are H2S and OCS with column densities both above 10 to the 17 per centimeter squared. The figure here shows you roughly the distribution of, for example, 34SO2 in this case, just one of the lines. You have to realize it's very tricky to actually make a very accurate integrated intensity map for line-rich sources such as these, especially if you have a velocity gradient. It's not so clear over how many channels you should integrate, so you have to be very careful with interpreting these. But essentially, most of the sulfur bearings have emission towards source B, towards source A, and to some degree along this so-called bridge that we have seen with pill survey extending from source A to B. To add on the spatial distribution, so many of the sulfur-bearing species aren't present only on the small spatial scales of the hot carino, but also on larger scales of the envelopes around the individual protostars themselves, but also in this circumbinary structure and this bridge that we see in the dust, and then is also very apparent in CO that you see here. So this is C17O, and then you can see that the C34S doesn't perfectly trace this bridge structure. It has a bit of an offset, and actually in terms of velocity, it also has a bit of a blue-shifted velocity in comparison to the quiescent bridge structure. So some of the sulfur bearings are also found on large scales, not per se associated to this dust bridge. And actually, interestingly enough, so our triple source, Iris 1693, also has a complex outflow structure, and there are reports of some sort of quadrupole outflow system, which perhaps is not so surprising if source A is a binary, as we've seen in the most recent data. But if you look towards this yellow point here, which is thought to trace an irradiated outflow cavity, at least from one of the outflows, not many molecules are detected there. It peaks in C3H2, but interestingly enough, it also has emission from H2CS, and C34S also shows up there, while not many other things show up there. So sulfur-bearing species can be interesting also on the large scales and not just the small. So for the rest of the talk, I will focus on what I obtained for the hot Carino, under the argument that this is the material that's most representative of disks scales. So this is probably the material that's being used for the formation of comets and protoplanets in this young system. So here I'm showing a plot of all the available D over H ratios. As I mentioned, with pills, we detected many isotopologues, including many deuterated species. Iris 6293 is quite rich in deuterium-bearing species. And you can actually spot that we also have some numbers for sulfur bearings here. My interpretation that if you have deuterated sulfur-bearing species, then this must apply that at least some of these must form early on at cold temperatures when deuteration is efficient. If I compare what I see for them in terms of what I see for other molecules, you can tentatively see some sort of trend that the sulfur bearings are agreeing better with my purple data points here, which are oxygen-bearing complex organics that are quite big, so bigger than 6 atoms. And otherwise, the sulfur-bearing data points seem to differ from all the nitrogen bearings as well as the small oxygen-bearing complex organics. So it's a tentative trend that we see here, but perhaps is telling us something about the sequence of formation of the different molecules. Okay, so let me now jump to Comet 67P. So the choice for Comet 67P is not the ALMA-PIL survey, but rather the ESA Rosetta mission to this comet. In particular, most of the results I'm showing are coming from the Rosetta Orbiter Spectrometer for Ion and Neutral Analysis, ROSINA instrument for short. The very exciting nature of Rosetta is that it monitored Comet 67P for nearly 2 years, and this allowed us to measure the variations in the chemical abundances in the coma of the comet and to derive really truly bulk abundances. Because comets are active, they have diurnal cycles, they have seasonal cycles. It's not so obvious that when you observe them from the ground on a certain day that you're actually getting something that's representative of what's the bulk in the nucleus of the comet. Now, with 2 years of data, this is a lot more likely, and so bulk abundances could be derived for the first time. One other thing that I should stress about ROSINA and why this instrument really provided some very unique data is the high mass resolution of this instrument. So one of the key specifications for it was that it could disentangle CO from N2 at mass 28. And so this really set a very high bar for the mass resolution, allowing us to identify various fragments accurately and thus be sure of the molecular identifications that are then carried out. So there was a whole zoo of molecules detected with ROSINA towards 67P, and this included the smelly and colorful sulfur-bearing molecules. So this plot you have already seen earlier. This plot summarizes the abundances of sulfur bearings and the different sulfur-bearing species that were detected towards 67P. So the typical known ones that we heard about already, and then the first-time detections for the comet, S3, S4, methyl mercaptan, and also potentially ethyl mercaptan. We can't be sure of the shape, but probably it's the ethyl mercaptan as the most stable one. So CS, as Dominique mentioned, tentatively, probably it's there, but the difficulty, it cannot be distinguished from CO2 at its mass peak. So it's not clear how much CS is there. And Dominique also already mentioned this morning that it seems that if we take what is now measured with ROSINA in the coma of 67P, so all this volatile sulfur, and we make a key assumption that the dust of 67P is the same as the dust of 1P Halley in terms of the S/O ratio, we sum this, then we do get the solar photospheric ratio of S/O, suggesting that in this way we have now really recovered all the missing sulfur. Again, under this assumption that the dust of Halley and 67P is the same, you can do some math and derive that in principle, this volatile sulfur is only 20% of the sulfur budget and 80% is in the refractories. So Diego, as you were saying, the majority is in the rocks. Now, if I compare what was found in 67P and the inventory of iris 16293, then I'm quite confident then with the pill survey, we recovered all the main volatile sulfur carriers with the exception of atomic sulfur. Now, atomic sulfur is a bit of a puzzle, which is argued to be an ice constituent for the case of 67P, but yeah, no information for it towards the protostar. So maybe this is one missing reservoir still there. Then isotopic ratios were also mentioned. So D over H and H2S was also measured, and this is a pretty consistent value through the course of the mission. So it seems that this value is pretty constant, so we can be quite confident of this. So if you want to derive the D over H, don't forget the factor of 2. And my plea to anybody working on D over H ratios, please explicitly state whether you're applying the statistical correction, because factors of 2 are starting to make a difference for us. So it's very important that you state this. Then, yes, there's also the measurements of the sulfur isotopic ratios. So it was already mentioned that if you compare relative to the terrestrial 33 and 34 sulfur, it seems that the cometary volatile sulfur is depleted in both, stronger depletion in 33S and a slight depletion in 34S. So these are these data points. And if we compare it to the dust measurements from 67P from a different instrument board Rosetta, then we also see that there's potentially also a difference between the refractory and volatile sulfur in terms of the S34 isotopic ratio. I do not have an explanation for this, but I think it's a very interesting result. So what I did look at already in detail is the correlation of chemical inventories between the protostar IRIS 16293 as obtained with the ALMA PILS survey. So on all the plots, this is your y-axis, and then the full chemical inventory that was measured towards 67P with the Rosina instrument. This is always your x-axis. And then I have split up molecules into CHO-bearing family, nitrogen, of course, our favorite sulfur, and then some chlorine and phosphorus-bearing species. What I claim is that we're seeing correlations in these chemical families. The correlation is somewhat weaker for the sulfur-bearing species. There are a lot of upper limits on this plot. However, I think all of these are suggesting that to some degree there is some preservation between this protostellar stage all the way into the comet, suggesting a partial inheritance of chemical material. And I said that the sulfur one is the weakest correlation that we have, and that yes, there are a lot of upper limits in this plot, which makes it a bit messy, but I do like to stress that it is an improvement of what we had before, and it's not only for 67P. Dominique, back in 2000, carried out an analogous piece of work for Comet Hale-Bopp, where there was also correlation seen in the other chemical families and a weaker one for the sulfur bearings. But I think with the improved data set, it looks better. So then there's individual molecular ratios we can probe as well to try to poke at the comparison a bit more. So you can consider the SO-SO2 ratio, which seems to agree for IRIS 16293b and the Comet, so 0.3 to 0.4, pretty good. Then you can consider the more complex species, so methyl mercaptan over the thioformaldehyde ratio. Here, kind of depends on what range you look at. You can have differences 0.7 to factor 5.3. For the case of the more complex ethyl mercaptan, I mean, we only have an upper limit, so this can be anything still. then I've also added this very interesting H2S over OCS ratio, which I will come back to at the very end of the talk, because this was one of the critical differences that was very apparent in the sulfur-bearing family towards these two targets. It seems that there's much more OCS than H2S towards the protostar than in the comet. So really, H2S seems to be one of the key sulfur-bearing species in the comet, and the protostar OCS definitely dominates. And then this is something that's reflected in the ratio. And yeah, Francois was intrigued by your correlation of methanol and OCS, so I computed that ratio as well, just to see what it comes out to. Okay, yeah, differences of 2 to 13. So, it seems that we have to think about what every single molecular ratio is telling us, and also we need to poke at the information hidden in the D/H ratios. So for the beginning, I'd like you to focus on just the pink points in this case. So the pink points are all the available D/H ratios with statistical correction measured in 67P. So when I first looked at the pink data points, I thought, okay, this kind of makes sense if I think about deuteration and kind of the sequential formation from diffuse to dense to collapsing protostar, because if you look at the values, then you kind of see lowest values for water, CO, CO2, H2S, and ammonia, kind of your first species that you expect to be formed in clouds. Then you get into your denser, colder cores, and then you start forming your first deuterated water, your deuterated ammonia, and then you start forming your methanol on grain surfaces as well. And then you get to the very latest data points close to the onset of collapse on the longest time scales, and then you start making your doubly deuterated water and also your deuterated methanol isotope logs appear. Hence, your doubly deuterated water and your methanol isotope logs give you the highest D/H ratios. So I thought this makes nice sense. But yeah, then you look at the blue data points, those are your IRS 16293 data points. And then you kind of run into a bit of trouble with this explanation, because you would expect to see the same trend, but yeah, it doesn't really work out so well for all the species. So it's in particular for doubly deuterated methanol, and of course, for HDS, we have some very firm and pronounced discrepancies in the D/H ratio. So this must be telling us something else besides just the same thing happening over and over again in the same system. Tentatively, you also see differences in the D/O ratio and NH2D, but okay, these you can argue away because they're not the best you could get for IRS 16293B in specific. So in my opinion, this could be a sign that there are environmental effects taking place here, that there could be cloud-to-cloud differences, and the cloud that IRS 16293 formed from, which is known to be quite cold, may really not be the same as the cloud that our solar system was formed in. All right, so then in the very last bit of my talk, motivated by this large difference between H2S and OCS that I saw between 67P and IRS 16293, I had an ALMA proposal that was partially observed in the end to probe this ratio in a sample of low-mass protostars. So in my original data set was targeting sources that we know are rich in complex organics and that have high abundances of all these species. And this contained IRS 16293 to get a very good line of H2S that was missing from the pills set, as well as IRS 4A and CRA 7B, an irradiated source. And then in the end, because the proposal was only partially observed, I only got ALMA ACA data, so we're probing in this case scales that are a bit more envelope size, so 6 arcsecond for all of them. The 12-meter data was never taken. We ended up combining this with data from Lukáš Tihoník as well, who by accident covered lines of H2S and OCS in additional 6 sources. And then we had a very clever master student working with us for 2 semesters who then actually took a look at this data and analyzed it. So this is our dust continuum sample of the source. So as you can see, for example, Iris 16293 that you see here, at this spatial resolution, it becomes definitely harder to disentangle A from B, but it's still manageable to probe the 2 separately. So what Tanya obtained after the analysis of the different lines, in particular for the line-rich sources that were part of my data, we again covered the rare isotopologues as well, because for those, H2S and OCS are optically thick, guaranteed. So covering the rare isotopologues was very helpful, just like with the PILS survey, to get the proper column densities. And then for the less abundant sources, most of the time we got away with just the observed main H2S and OCS lines. So what Tanya did was analyze the data and compute the ratio for all of these and then compare what we get. So what we see here is that our data points are spanning an order of magnitude, even in this relatively small sample of low mass protostars. We don't particularly see a dependence on binarity, if it's a tight binary or a wide binary. Again, this might be pointing us to suggest that it's the natal cloud conditions that are playing a critical role at setting this ratio. So be it either the different temperature or the different UV flux that they're being exposed to. Then on this figure, we also added what was determined for Comet 67P. So it's the black dashed line, and the colored region is the error bar on this value. So the cometary value can be anywhere here. You can see that there is only BHR 71 that is getting into the cometary range for this ratio. Everything else is well below. And then we also added the 2 available upper limits from the direct infrared observations. So upper limits owing to the non-detection of H2S ice directly. So it seems that if we compare this, there's only really one source that potentially is getting to the amounts that are being seen in the comet and in the area of the upper limits for the ices. And the one thing that sets this source apart from the rest is actually its natal core. It's a very isolated environment where it is, so perhaps it is indeed colder and less irradiated there, and then this is helping you to boost this ratio upwards. So warning, this is preliminary. We're hoping to have this submitted in about 2 weeks, but yeah, small changes still pending. Okay, and then this brings me to my final slide. With some take-home messages as well. I also opted out of the word conclusions. So, first of all, comets, I think, keep a partial record of the physical-chemical evolution of the planetary system. I think this is being demonstrated by the correlations that we're seeing between star-forming region and comets, and I think this is also something seen in the sulfur-bearing volatiles. I think there's support for at least some volatiles being initially made in prestellar cores. This will include some complex organics, and I think the evidence for this comes from the isotopic ratios, in particular the deuteration, such as that of H2S and H2CS. I do agree that there's some chemical alteration still happening en route from core to disk. Perhaps ratios such as the H2S over OCS could be a potential tracer of this processing. So I would like to thereby thank you for your attention, and please have a look at the papers that are to come.
Thank you very much. Very nice. In one of your slides, when you have a ratio of
oxygen, carbon, sulfur species, there is a large uncertainty in between. Okay, go back again. Between 12 and 13. There, that one. So it has called my attention that the uncertainty is very large whenever you have an oxygen atom in the molecule. So you see the last one. No? So the ratios are comparable. Differences of between 12 and 13. Can you constrain this uncertainty with some models, and not giving such a large range of ratios?
You mean for the cometary numbers?
Yeah.
So these come from the direct measurement and inspection of the data at the different points in the mission. So some of these are instrumental. I doubt that they can be constrained better than this.
But does this range reflect variation in the production rates and the maybe surface chemical processing, or even the inner coma where you have some chemical reactions?
So for some of these, the photodissociation has been accounted for. I think for the cases when the rates are available, it has been accounted for. I can't remember off the top of my head for which ones. But these are already, to add, are bulk values. So this already contains a degree of averaging. So if you would look at instantaneous, I think the errors are even bigger, actually.
Bigger. Okay. Thank you.
Hello, nice talk. I was wondering, I'm not sure which kind of H2S lines you detect in your frequency setups, because it's 300 gigahertz, no? But yeah, my question is, do you take lines from both ortho and para H2S? And is anybody in the community discussing the ortho to para ratio, protostars or in comets?
So yes, so for H2S at the pills range, there's, I think, one line with a way too high upper energy that's not detected. So in the follow-up data that Tanya was analyzing, there we moved to band 6, and there we had the 216, and then we had the isotopologues as well. So from those lines and from the isotopic ratios, so it's the 33S, the 34S that we use, not the deuterated. And then we infer the H2S line. Yeah, and then, so no, I take them both together. I don't think that has been separated. But yeah, I wonder if that has additional clues as well. So I haven't touched this.
Just a question. In this plot in where you compare a lot of deuterated molecules, all of them have all of them been observed using interferometric observations?
Is this the plot?
Yes.
So all of this is from the ALMA pills survey. So all of these are interferometric data points, except for HDO, which is, I believe, observations more towards source A, because for source B, the data is still an analysis by Audrey Couton at higher bands. But otherwise, these are all the same data sets, so exactly same positions, same beam, same
it's
setup.
great. Because in your previous slide, I missed at some point because you say that you don't detect any deuterated species. Here, I think it's in. Okay, no isotopolog detection. What does
no CH3S.
Not in CH, but yes in the other.
But
okay, now I understand. Thank you. Thank you very much, Maria. Well, this is our last talk because we have an outreach conference at 7 o'clock in the planetarium that, I don't know, Giuseppe Miguel is going to to give the conference. So of course, all of you are invited to attend. And well, I think that we can close today and start again tomorrow morning at 9 o'clock. I think that 9 o'clock is very early in the morning, but our ultimate goal is to be able to finish around lunchtime, okay? Because tomorrow is Friday and some of you want to take the train to Valencia, I think. There are some persons that take the train to Valencia. So I think it's better to keep 9 o'clock and try to finish at lunchtime. Many thanks.